Just gonna wait to see if it's streaming. I think I have to be on the page before it starts. Okay, no, it's working. So I'm gonna take a break from what I was doing from the um, trying to build the poker tool to study some data structure and algorithms because I think I need to upgrade my skills on that. I'm gonna spend, I think, 50 minutes and then take a break. And then I'm gonna train the command line thing. I think I still have 5 days left until 29 is the last day, so I'm gonna spend some time training this to take advantage of that uh, until I have it. And then I'm also gonna learn, spend more time going over the Italian keywords because I'm not doing that very often. I only do it when I stream. So, and I feel like I'm not really remembering very well the words that I learned. So maybe I'll try a different approach as well. Try to maybe type the words after I go over them, or try to do something so I remember more, or maybe just be more consistent and do it every single day. So because otherwise it's gonna take too long. But I think after I learn the first 1,000 words, it's gonna be easy to learn everything else because those 1,000 words that I got are the most frequent ones, so are the 80% that are used more often. And I think that people, when they're speaking, they're probably using those words, and the other ones are not that important. So I think after I understand all of them, it's gonna be enough to understand the conversation. And maybe after I go over all of them, then I start watching videos, but I'm not really sure how much I want to go into that. I definitely do want to learn different languages so I can expand my horizons because I different languages are kind of like portals, and I really sense that because my main language is Portuguese. So after I learned English, now that I know English, it feels like a whole new universe is open up. And obviously English is different because most of the world speaks English. But I think that's the same with other languages. You can just increase and expand how much information you get and change the way you think. So it's probably good overall. But yeah, so I'm gonna start the timer here. And I think I'm gonna go over this list here of graphs. I don't think I think I'm gonna go more on how I feel about it instead of putting a timer. I'm gonna try a little bit and then I'm gonna look for the solution if I can't. If I sense that it's getting too hard and annoying to do it, then I'll look for the solution and move on to the next. And I'll try to do as much as I can until I feel like I understand really well how it works. And I don't know exactly how this playlist works here, but I think you just you can go after you solve, it opens the other ones that are locked, but I'm not really sure. I also don't think I'm gonna put music anymore because I don't want the channel to be striked or taken down. And I got a warning last time I did a stream. I still was able to upload the video after, but I think just to be safe, I'm not gonna play any music. I'm gonna play music on my side, but then mute it on the stream. I think I'm gonna do it with Python initially, then maybe once I feel confident or once I'm better, then I try to do it in Rust instead. I wonder if I can do this here. It's a good idea.
You are also given three integers sr, sc, and color. You should perform a flood fill on the image starting from the pixel image SRSC. To perform a flood fill, consider the starting pixel, plus any pixels connected 4-directionally to the starting pixel of the same color as the starting pixel, plus any pixels connected 4-directionally to those pixels, also with the same color, and so on. Replace the color of all of the aforementioned pixels with color. Return the modified image after performing the flood fill. Example 1. Input, image equals 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, SR equals 1, SC equals 1, color equals 2 output, 2, 2, 2, 2, 2, 2, 0, 2, 0, 1 explanation, from the center of the image with position, SR, SC, equals, 1, 1, i.e., the red pixel. All pixels connected by a path of the same color as the starting pixel, i.e., the blue pixels, are colored with the new color. Note the bottom corner is not colored too, because it is not 4-directionally connected to the starting pixel. Example 2. Input, image equals 0, 0, 0, 0. You should perform a flood fill on the image starting from the pixel image SRSC. To perform a flood fill, consider the starting pixel, plus any pixels connected 4-directionally to the starting pixel of the same color as the starting pixel, plus any pixels connected 4-directionally to those pixels, also with the same color, and so on. Replace the color of all of the aforementioned pixels with color. Return the modified image after performing the flood fill. Example 1. Input, image equals 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, SR equals 1, SC equals 1, color equals 2 output, 2, 2, 2, 2, 2, 0, 2.
I don't understand the description. What do they mean by connected far directionally to those pixels? So should I take into account all the pixels? If that was the case, if I should take into account all the pixels that are directly connected to this one, then this one shouldn't change color here because these ones are 0. And if it's just to change, then it's really easy. I should just loop twice to go over all the elements and then make an if statement and change the color based on whether or not it's 1 or 0. Oh, the center is SR, SC. And this is the main problem I have with these problems is that a lot of the times it's hard to do them because of the description, not necessarily that the problem itself is hard, which is really annoying. Because then it becomes something about thinking, trying to figure out what exactly they want instead of figuring out how to create the algorithm that is gonna solve the problem. Mm. Or maybe I should do this instead. And then image ij. And that's probably the brute force approach, which is probably not the best. But you just go over all the elements and then you place the if else statements to find this far directionally here. And then you change based on the value of the center one. So if the node is equal to the value, then you put the color. You make the value equal to the color. I just don't understand what is far directionally. Because that's gonna change the if else statements. I think I'm gonna look at the solution and move on to the next one.
Input, image equals 1, 1, 1, 1, 1, 1, 0. Approach number 1, depth first search accepted. Intuition. We perform the algorithm explained in the problem description, paint the starting pixels, plus adjacent pixels of the same color, and so on. Algorithm. Say color is the color of the starting pixel. Let's flood fill the starting pixel. We change the color of that pixel to the new color, then check the 4 neighboring pixels to make sure they are valid pixels of the same color, and of the valid ones, we flood fill those, and so on. We can use a function DFS to perform a flood fill on a target pixel. Complexity analysis. Time complexity, O, n, where n is the number of pixels in the image. We might process every pixel. Space complexity, O, n, the size of the implicit call stack when calling DFS.
This is Java. Don't understand why. Oh, it's gonna return because that's the bottom, the last case. I think. Maybe not. I don't understand why it returns the image here when they're both the same. The new color is equal to the color of the center. Hmm. So that's the part that I wasn't understanding really well. I think I remember looking at these problems, and this is a common thing that people do, which is breadth first search and depth first search. And then I remember seeing this pattern a lot as well, where you get the length of the two sides, the columns and the rows, and then you perform if-else statements based on the length, the rows and the columns, and if-else conditions, and that seems to be the pattern of depth first search. So we have a flow of if-else statements based on based on column and row, and then you do whatever you want to do, and then usually you put the case that you want the code to stop the search at outside, because you're calling the function multiple times, but here I don't think that's the case because it's only recursively calling the DFS and not the main flood fuel function. So I guess that's just the condition that the problem asks for, but I didn't understand that as well. This color equals new color return image doesn't make sense to me. And then here it just tells which direction to go based on the node that is at, I think. It starts from the center. I guess that's why it's probably difficult to do it, because you can start from multiple different positions actually, and then you have to figure out which ones you're gonna paint. I just understand the four connected thing. Didn't understand that. Yeah, I'm gonna move on to the next. Hopefully I can go to the next without. I guess I can just copy the solution there and put on mine. Maybe it's not gonna let me do the other ones though, because it might require the paid version, the premium version on Lit Code. One thing that I'm thinking about doing as well is I might just search for the list of common of all the well-known graph algorithms and then get all of them and study them. And then I can think about practical applications to them instead of doing these exercises. Because a lot of the times I don't like doing them because I don't see the point. It seems like a waste of energy, but
Given an MXN2D binary grid which represents a map of ones, land, and zeros, water, return the number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically.
it might be the case that I'm rationalizing as well, and it's just because I don't want to spend energy trying to get out of my comfort zone and learning how to think about it in this way. But yeah, I think that's the challenge though. I need to find a middle way between doing these exercises, which are kind of pointless because I'm not invested in finding the solution, and at the same time, I want to learn the data structures and algorithms, how to think more about it in a way that is uh, more algorithmic. Algorithmic.
You may assume all four edges of the grid are all surrounded by water. Example 1. Input, grid equals 1, 1, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, output, 1. Example 2. Input, grid equals 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, output, 3. Constraints. M equals grid.length. N equals grid I.length. 1. Grid ij is 0 or 1. Accepted. 1,926,007.
Hey, bro. Yeah, this seems hard to do as well. I assume it's just gonna be the same thing from the previous one. You do that first search, and then you put the conditions, and the challenge is figuring out how you put the conditions so it gets all the edge cases. Just trying to think which one is the rows and which one is a column.
One million nine hundred and twenty-six.
I think it's the other way around. Yeah, okay. So this is probably gonna take the positions. This is the thing that I don't know what to do. So how should I organize the search here? Which conditions to put? Let's say 0, 0, the first position. So I can't really make if x equals to y, I think, because there are multiple different positions. I guess I can use the rows and columns. Like this. And here I might get a warning because I don't have else statements here, but maybe I'll do it like this, just save some time. I can't be bigger. I guess it depends on which position I'm gonna start as well. So I'm thinking about starting at the 0, 0 position, but I'm not sure if the indexes go down as well. I don't think they do. I think it's just up, even though. So the one Y index is gonna go from this one to this one, I think, in the vertical direction. So it's going down, but it's actually positive. I guess I have to put like this and Y greater than. I don't remember really well. I know I have to do something like this. I guess it's the other way. I remember doing some of this a while ago, and it was whenever one was smaller, the other one has to be bigger, and then you call the function again. So here's probably the same thing. And what this is gonna do is gonna go over all of the elements of the matrix. Y plus 1, something like that. And then I need to put a condition to see, to cache the values. And how am I gonna know if it's an island or not? That's the question. Because the number of zeros around might change. But this problem is much better than the other one, at least, because it's very clear what I have to do. So when is it not an island? Like, is this one an island here? Surrounded by water and is formed by connecting adjacent lands horizontally or vertically. So I guess this whole thing is one island. No, because this has 3. So it should be 1, 2, 3. Hmm. So I guess vertically it doesn't count, but here it says it counts. So maybe the condition for finding an island is if it all. But no, that's, I would say all the adjacents are zeros, but that's not true. It might be either 0 or they don't exist, but I don't think that's true as well. But maybe it is actually. If the horizontal and the how I'm gonna know that? That's the question. Can use the positions of the grid. The current one is the one being analyzed here. Then left would be Y. But there must be a better way to do this. Because here I'm gonna have to put this on a try except block because it might not exist. So I suppose I should do it based on the rows and columns. Yeah, I should do this stuff instead of these if statements here, where I get the position of all the adjacent ones, and then I check to see if they are 0 or not. how do I find the ones that are on the periphery here? I find them by making the condition based on the rows and columns. So maybe that means that I'm either here or here, I think. No, the rows are I'm messing up, I think. The X and Y is confusing because to think about which one are the lines and which ones are the column. Yeah, the rows should be the Y actually. It's the other way around. Yeah, so this case is when x equals 0 or x equals r. It's these elements here and these elements here. And then y less than or equal to columns is just so I don't pass on the columns. But I think I'm thinking about this the wrong way because there must be an easier way to get the adjacent ones for every single iteration. I'm just trying to think about that. I don't think it's very difficult to solve. It's just a matter of understanding um, how do you get the adjacent ones each time. Then after you have the adjacent ones, you make the condition to see if they are 0 or 1. And then if if the adjacents that are not that exist in the graph are all 0, then it is an island. But yeah. So it only counts an island when you have one at least or one node that is connected by zeros on the horizontal and vertical. But this is not because it's 1 and 1 here, so it doesn't make sense. Hmm. I guess I need to put this separate as well, now that I think about it. Because if I'm gonna get, I need to know if they're on the left or on the right. So I get the correct nodes. Because I don't think I can put a condition, just say, it doesn't make sense to put a condition that says that the node doesn't exist. I think you can do that, but it doesn't make sense. Yeah, so these would be the ones. So the ones on the right are gonna be equal to the grid x plus 1 and y. Yeah, but the vertical, I have to put, just think about the condition of the y as well. So y has to be greater than 0 or hmm. I'm thinking about this the wrong way. I think the logic that I'm putting is the right way, but the conditions are not the correct way because the way that I'm thinking about it, I'm gonna put it so too many conditions to check to see each node, and I don't think that's the right way to do it. And that's the first thing that I have to do. Then I have to think about the island. So what I'm trying to figure out is what is the best way to make the conditions here so that I check the adjacent nodes each time. I think I'm just gonna search this up actually. Yeah, this doesn't have what I want.
Today, I'm going to teach you depth first search. Depth first search, or DFS, is an algorithm for searching a graph. As the name implies, we'll use DFS to search a graph vertically before we proceed horizontally. When you think of depth first search, I want you to remember a stack, as this is the data structure that keep track of vertices we'll visit. Let's perform DFS on the following graph. We want to know all the nodes that are discoverable from the node A. Along the way, we'll keep track of two things. First, nodes we visited will be colored black. Nodes that are in the stack that are in line we visited will be colored gray. Starting our algorithm, A is the first node we'll visit. We'll keep track of the stack in the top left corner. We pop A from the stack and mark it visited. We also add its adjacent nodes into the stack. I'm adding the rightmost initial voiceover. On the left, notice the reversed function that adds the rightmost node into the stack first, so we visit it last. If the adjacent node has not yet been visited, we add it both to the visited list approach here because I think it's easier to follow. For example, in the worst case, we're going to visit each of DFS plus the number of edges. Please subscribe and share.
In this video, we will take a look at our first graph algorithm, depth first search, or more informally DFS. This algorithm is one of the most fundamental algorithms in graph theory, and many of the ideas in this video will carry over to more advanced graph algorithms. For that reason, in this video, I'm going to spend some extra time building intuition for the ideas behind this algorithm. Here's what you can expect to get out of this video. We will first introduce the concept of a graph traversal and what that even means. Then we will try to build our own graph traversal method and show how it intuitively leads to the core ideas of depth first search. Once you have an idea behind what depth first search is trying to achieve, we will then spend some time going through the implementation of DFS in a visualized manner. And then we'll finish off this video with some really cool applications of depth first search that I'm sure you're not going to want to miss, so make sure you stick to the end of the video. Let's get started. Given a particular graph, one useful ability involves starting at a single vertex and finding a way to get to every other vertex of the graph. The formal name for this ability is a graph traversal, which is simply defined as an algorithm that visits every vertex of the graph. There are several graph traversal algorithms, and they are primarily differentiated by the order in which they visit vertices. In this video, we'll focus on the DFS ordering. So now that we know the basic idea behind a graph traversal, let's take a step back and see if we can sort of invent our own graph traversal. The line of thought that I'm going to present here is actually exactly the DFS algorithm. The goal here is to show you how the DFS algorithm is really a surprisingly intuitive idea, something that with some thought you probably could have come up with on your own. Let's take a crack at it with this graph. Given a start vertex, we want to find an order that we can go through the vertices of the graph so that we guarantee that we end up visiting every vertex. Let's start with vertex 0. From vertex 0, we have a couple of options for how we might want to continue. The option we choose doesn't really matter too much here since our hope is that we'll eventually explore all the vertices anyway. Let's say that we choose to visit vertex 1 from here. What now? Well, now that we're at vertex 1, we have a new set of choices for where to go next. It doesn't really make sense for us to go back to vertex 0 since we've already seen it, so let's pick a new vertex to explore. Let's go with vertex 2. And from vertex 2, we only have a couple of options, namely going to vertex 0 or vertex 1. But we've already seen those vertices, right? So what we might naturally do is say, okay, there's nothing further we can do from this vertex, so let's take a step back to where we came from, which is vertex 1. And from vertex 1, we now have two unexplored vertices that we can then go to. Let's go to vertex 3. From vertex 3, our path forward is pretty set in stone. The only unexplored node is vertex 5, so let's go there. From vertex 5, we have a few options on how to continue traversing the graph, and let's go ahead and pick vertex 6. At vertex 6, we've now reached another dead end similar to what happened with vertex 2, so let's retrace our steps back to vertex 5. From vertex 5, let's say we pick vertex 7 as the next node we visit. From vertex 7, the only path forward is to vertex 8, and from there, we again have only one choice leading us to vertex 9. At vertex 9, we've now hit another dead end, so let's go back to vertex 8. Now what's different this time is that from vertex 8, we have already explored everything there is to see, so let's retrace our steps once again. We got to vertex 8 from vertex 7, so let's go back to there. From vertex 7, we have the same story, so we go back to vertex 5. And everything from vertex 5 has been fully explored, so from vertex 5, we now go back to vertex 3, which is the vertex that got us to vertex 5. Same story here, so let's take one more step back to vertex 1. And now that we are back at vertex 1, we have finally found a new undiscovered vertex, so we now visit vertex 4. From vertex 4, there's nothing new to explore, so we go back to vertex 1, which now also has nothing more to explore, which finally leads us back to vertex 0, which now is also completely explored. And now that we're back to where we started, that's how we know we have traversed every vertex of this graph. So I know that was a lot, but the philosophy of how we explore this graph, but continuing to explore new vertices as we see them until we hit a dead end is what depth first search is all about. When performing depth first search, think of yourself as a bold and adventurous explorer, where every time you see a new vertex, you will continue to explore new vertices until you hit a dead end, in which case you'll retrace your steps and continue exploration. It's worth noting that there are actually several valid depth first search orderings for this graph. Let's go through one more valid ordering as an example, and also as further familiarization and practice with the core idea behind DFS. We can generate another ordering by just changing up the choices of vertices to explore whenever we have a choice while sticking to the core philosophy. Let's start again at vertex 0, but now when we have a choice between choosing vertex 1 or vertex 2 as the next node to explore, let's pick vertex 2. Last time we went through this, if you remember, we picked vertex 1. Again, I want to emphasize that both of these choices are valid, and if you were ever asked for the DFS order on a test or an exam, the instructions must be clear on how to make these choices. A common way to do this is to enforce the constraint that you must always pick the node with the smaller value when you have a choice. In that case, we would have picked vertex 1. Anyways, back to what we were doing after visiting vertex 2, we only have one choice, which is now to go to vertex 1. From there, let's say we now visit vertex 4, which then leads us to a dead end, so we go back to vertex 1. Now the path forward leads us to vertex 3, which then forces us to visit vertex 5, where we now have several choices. Let's pick vertex 8 this time. From there, we'll choose to Let's now talk about implementation. It helps to try to figure out the implementation on a smaller graph since it has fewer moving parts. Here's one valid DFS ordering for this graph. One thing that you may have noticed about this process through the examples that we've done so far is that it's actually naturally recursive. We start at a particular node, and once we visit that node, it's almost like we can ignore that node in the graph and run DFS on all of the neighbors of that node. So this inspires one initial idea for how we might implement DFS. Given a particular graph G and a starting vertex V, we first visit V. Then for each neighbor of node V, we can run DFS on the graph with that neighbor as a new starting node. Remember that we are representing graphs using adjacency lists, so an operation like finding the neighbors of a node is quite simple. So let's try the first attempt at an implementation and see what happens. We start at vertex 0, and let's say that the first neighbor we end up picking is node 1, so that's the next node we visit. We then go through the neighbors of node 1 and repeat the process. But there's one big issue with this implementation. Take a second to see if you can figure out what the problem is. The issue here is that when we iterate through node 1's neighbors, one of those neighbors is node 0. This means that with this current implementation, we'll end up calling DFS on node 0 once again, which would create an infinite cycle of recursion. So how can we fix this? Well, what we want to do is ideally only call the DFS function on nodes that we've never seen before. One way to do this is to essentially mark nodes that have already been visited. We can do this by maintaining a list of Boolean values where each one is mapped to a vertex of the graph. Initially, all these values will be false since we haven't visited any vertex. But as soon as we visit a vertex, we can mark the vertex as something we've seen before by changing the respective index to true. Now with the vertices marked appropriately, we can now call DFS recursively on a vertex if that vertex is not currently marked. Let's dig a little bit deeper to verify that this implementation actually works. We first call the DFS function on our graph with starting vertex 0. This will then visit vertex 0, giving us the first vertex of our traversal. After that, we mark the vertex and begin looping through the neighbors of vertex 0. Let's say the first vertex from our neighbors we look at is vertex 1. What happens now is that we make a recursive call to our DFS function with a new starting vertex of 1. The first thing that happens in this recursive call is we visit vertex 1, which becomes the second vertex in our DFS traversal. Now the key idea is that when we look at the neighbors of vertex 1, vertex 0 is already marked, so we can't make another call to vertex 0. So the only remaining option is to recursively call a function on vertex 3. The process is exactly the same. We visit vertex 3, which ends up being the third vertex in our DFS traversal. Now from here, we can go to vertex 2 or we can go to vertex 4, and the choice we make here is arbitrary. Let's say the algorithm picks vertex 4 first. This means that we have another recursive call with the starting vertex now assigned to vertex 4. We then visit vertex 4, which is the fourth vertex in our traversal. Now at this point in the recursion, we now look at all of vertex 4's neighbors, which includes only the vertex 3. But notice that vertex 3 is already marked, so what that means is at this point there's nothing further to do in this call. So we go back to the previous call of the DFS function on the starting vertex 3. We just finished our call to the neighbor vertex 4, so let's now evaluate the next unmarked neighbor. The only remaining unmarked neighbor is vertex 2, so we can make a recursive call to the function with starting vertex 2. In this recursive call, we visit the vertex, and that becomes the fifth vertex in our traversal. There are no more unmarked neighbors for vertex 2, so we can go back to the call on starting vertex 3. Vertex 3 also has no more unmarked neighbors, so we can go back to the call on vertex 1. Same story here, so we go back to our first initial call on vertex 0, which also has no more unmarked neighbors, which means at this point the DFS traversal is complete. Pretty elegant and simple algorithm overall, and I hope drawing out the recursion gives you a better understanding for why this algorithm works. There's one more implementation of DFS that I think is equally important to understand. This is an iterative implementation where we have the same concept of marked nodes as before, but the key difference now is that we will use a stack data structure to keep track of nodes to visit. So at the start, we will initialize the stack with just the starting vertex, and then while the stack is not empty, we'll pop off the last vertex of the stack. If that vertex has not been visited before, we will visit the vertex and mark it, move this vertex from the stack, and loop and pop off the last inserted vertex to our stack. But since
We should become better at thinking about recursion as well. I think that's the main problem I have with solving this. Is very hard for me to think about recursion when I'm thinking about how I'm gonna solve the problem. It's hard to put on my mind through each loop what's gonna happen next time the function is called. It's not intuitive at all to think about it that way. It's a lot easier to think about the for loop, because the for loop you don't have to think about all the other stuff that is gonna be involved. I mean you do, but it's very different than with calling the function. And this here also didn't help at all, because it's not the same thing that I'm trying to do there. Because I get the logic, and I think it's kind of pointless to spend a bunch of time talking about that as well. And it's kind of obvious that you want to go through all the nodes, but I want to understand how to think about the flow of if-else statements to go through all of them. Trying to think about how I can find a video or maybe something that talks about how to find the nodes that are on the edge. I'm definitely I remember I'm definitely sure that there is a way that you put 4 different conditions, and it's four if statements, and then you call recursively, and that explores all the nodes, but I don't remember really well. That's what I'm trying to remember. Because after I have that, then I can think about the island, the conditions to find the islands, and then store the islands.
vertex 3 has never been seen before, we'll put it in our stack. Notice that vertex 3 shows up multiple times in the stack, but that's okay. The mark this vertex. But at the same time, including the iterative approach is important since it's more generalizable to other graph traversal algorithms that require an iterative approach. You end up seeing this logical structure a lot in other graph algorithms, so I think it's a good idea to introduce it here. On the topic of comparisons, let's make a quick note about the differences between a pre-order and post-order DFS traversal. The orders we have looked at thus far are all pre-order DFS traversals. All this means is that we output a vertex as part of the order as soon as we encounter a new vertex. A post-order traversal vertex where we hit make sure you understand that a DFS is visited requires running DFS multiple times. The main idea behind finding connected components is in the last part of this video, I want to talk about after all its neighbors have been visited. This idea is reflected by just moving the call to the visit function to the very end of the DFS post-order function. And that's all there is to DFS post over. You have a cycle. Another example, graphs. Imagine each vertex reversal of a graph will always of a node.
I actually didn't like this video that much.
Hello and welcome. My name is William, and today we're moving on to talking about the depth first search algorithm, which plays a central role in several graph theory algorithms. So what is a depth first search? A depth first search is a core algorithm in graph theory that allows you to explore nodes and edges of a graph. So it's a form of traversal algorithm really shines. A depth first search. So a depth first search, how we arbitrarily pick node 7 that are currently being visited. To go to node 3, then pick node 3's last edge. So this was one to get a deeper understanding of how
Hmm.
it worked. A, containing true or false, so I check the base depth first selected component to identify a like you do a depth first, also label it with a recency list and our visited array. But additionally, we'll also need a variable called count that tracks the number of connected components and an integer array that holds the integer value of which component a node belongs to. Inside the find components method, we loop over every node and check if the current node has been visited or not, and then execute some logic. This depth first search variant differs slightly from the previous in that we execute a depth first search for every unvisited node. When we actually do the depth first search, we visit nodes and mark them as visited. So we never revisit the same node more than once. We either skip over a node because it's been visited in this for loop, or start a depth first search there. If we start a new depth first search, visited and connected components. But we can augmentation points, find augmenting paths in the flow network, generate mazes,
I
and many,
can
many more.
run the nested loop as well, now that I think about it, to find out the nodes, but that's not the point of doing this. I want to figure out what to do with recursion on that first search.
Today we are going to talk about recursion. I think most computer science students would agree that recursion felt more confusing than your average computer science topic. In this video, I'm going to show you 5 simple steps that you can use to help you tackle any recursive problem. And hopefully, these steps will help you realize that in reality, recursion isn't actually that bad. I'm going to show you how to apply these steps in the context of solving 3 specific recursive problems, each of them progressively more difficult than the last, so make sure you stick to the end of the video. And as always, I think you'll get the most out of this video if you take the time to pause and ponder some of the problems that we worked through and the steps we went through to solve them. So, without further ado, let's get started. Suppose we want to solve the following problem recursively. Write a function that given an input n, sums all the non-negative integers up to n. Here's a couple quick examples of inputs to this function to give you a sense for what we're trying to implement. A lot of you may have seen an iterative version of this function, or even a mathematical version of it that we went through in a previous video. But if you had to solve it recursively, how would you do it? Recursion is...
The other thing that I think I can do is just return. So call left and right recursively. I'm thinking about changing the names here, so it's more intuitive, but I don't think I'm gonna do that. And maybe it's greater as well. And then I can make left equals DFS or y minus 1. I don't know if that makes sense. Yeah, and then I put some if-else statements to see if the current. That's the difficult part, how I'm gonna check to see if I have an island or not. I think I need to create a different matrix outside and then check to see uh, update the matrix in each iteration or create a cache or something like that. And then if meets the conditions, then it's still an island, but I only upgrade when it's not, when it stops being an island. The difficult thing is thinking about what condition can I use to check if it's an island or not. And I have no idea. Oh, all four edges of the grid are surrounded by water. So the edges are 0. Also trying to think if this condition here is gonna stop from the current one being. So let's say that x is low as. I just realized that I put. Let's say that x is lower than 0, but then it's gonna hit this condition first. I guess it doesn't matter. Yeah, I don't think it matters. But I don't think that that's a good way to do it as well. It's probably better to put the conditions here and call the function only once at the end, recursively. Because this way I don't think I'm gonna be able to put the if-else statements to check if it's an island or not. I guess what I can do to see if it's an island is to check every time I have a 0, I check I don't know how to say that in English. I think it's perimeter of the island. Yeah, this is hard. I have no idea. I just saw this. I think I'm gonna take a break because the timer stopped a long time ago. I'm gonna train this stuff here and do the Italian thing. Maybe I'll watch one more of these videos before. I
In
think
this
I'll watch
video,
these 2 videos and then I'll take a break.
McDowell, author of Cracking the Coding Interview. Today I'm going to solve the connected cell problem. So in this problem, we have a matrix of zeros and ones, and we want to find the largest region of connected ones, where that's defined to be ones that are adjacent to each other, either looking horizontally, vertically, or diagonally. So depth first search is perfect for this problem. We could use breadth first search instead, but generally we find depth first search to be a little bit easier to implement, and it works just as well, so we might as well use it.
Oh, this is
So
the
we're gonna do this
solution, I think. A slightly different problem, but yeah. I think I'm gonna watch it anyway.
Matrix, and every time we see a 1, go do depth first search on that region and get the size of it, tracking the biggest region as we go along. So pretty simple, basic for loops. By the way, I always find it's best to not use x and y when we're dealing with matrices, because what I find is that people think that x should be the row and y should be the column, and that's actually backwards. So just take it from me, don't use x and y as variable names. Row and column are really better choices. Okay, so if matrix row and column is 1, then do a traversal here, so do a depth first search here, get region size, matrix, row, column, and then max region. Basically update the max if necessary. The size of max region. Okay, so one thing I want to be sensitive to is not that we're not repeating work necessarily. So if we come across a 1 in the same region multiple times, which almost by definition we will, we don't want to repeat the same work in the same region. So there's different ways of doing this. One is we could have some sort of like Boolean visited matrix like this, and every time we search some, I'm just putting links there of course, but every time when we're doing get region size, pass in this visited list and make sure that visited is updated not just for this row and column, but for everything else in the matrix, or everything else in that region. And that will work, but it's actually kind of unnecessary. If we're okay just storing matrix, then let's just reuse that. And every time we get to a value in this region, just update matrix and clear that to make it a 0. And that'll avoid this issue. If we're not okay with destroying matrix, then we can just clone matrix. Ultimately, it's kind of the same thing in the end. Okay, so now let's turn to region size. So get region size is going to take in the matrix and the row and column, and then it's going to do a depth first search. So it's going to search out recursively from each of those areas. So first thing I want to do is my boundary checks. So putting these boundary checks here, returning 0, so the region size is 0. So then what I want to do is I also want to check to make sure this is actually part of the region. So if matrix row, column is 0, return 0. So now comes kind of the interesting part. So the size of this region is going to be 1 for myself, plus the size of the region if I traverse up, down, left, right, diagonal. So initial size is 1, and then traverse. So there's different ways of doing this. I'm going to do it like this. So I'm going to search from row minus 1, because I have to go in actually 8 different directions, so all around. So row is less than, well, row, to start off R with row minus 1, R is less than or equal to row plus 1, R plus plus. So go through all 3 different rows, all 3 different columns here. Minus 1, column less than or equal to C less than or equal to column minus 1, C plus plus. And then search. So there's going to be size, so increase size by that area. So matrix of row, column. Then return size. So here I did not have to put in any boundary checks because I've already done all of that here. So it makes my code a little bit shorter. I could, of course, instead check the bounds before I traverse, or before I curse, but it's easier just to do it up here. And then I also want to make sure that I don't go search myself. I mean, I guess I could, but it's probably a little better so that I don't do that. So I'm going to just skip over myself. So if, yeah, I'll do it like this. If row does not equal to this and column or column does not equal to this. So make sure that one of them isn't equal so it's not myself. Then do the search. And then the other thing I need to do is I need to track some sort of way. I need to know that I haven't repeated this search and seen the same cell before. So I'll do this. Right after I check to see if this is 0, I'll clear this out. So set row and column to be 0. So what's interesting here is that this will actually serve dual functions. It'll do a is visited check for this depth first search and make sure that I haven't, I'm not running some sort of cycle in the search. But it'll also fulfill a value here on get region in that it'll make sure I'm not searching the same region multiple times. Now let's just look through this. Oops, this should have been matrix that.
Let's see how we can find the maximum number of connected cells in a binary matrix. We will also solve this connected cell problem in HackerRank website using Python language. Consider a binary matrix like this. We have each cell of the matrix filled with either 0 or 1. We will be writing a program to find the maximum number of connected cells having value 1 in the matrix. Here, we have 4 regions in the matrix containing value 1. Out of the 4 regions, this region has 7 connected cells having value 1, which is the maximum number of connected cells in this matrix. In our program, first we will set a maximum cell counter with initial value 0. Then we will start iterating through each cell of the matrix. When we find a cell with value 1, we will consider it as a new region and set the region cell count to 1. After taking the count, to mark the cell as visited, we will change its value from 1 to 0. After that, we will check whether any of its neighbors having value 1. If no neighbors are found, we will check whether the current region cell count is greater than the maximum cell counter. If yes, a new maximum cell count is set. If neighbor cells are having value 1, we will continue this operation for the neighboring cells too. We will continue with the iteration in this manner. After iterating through all the cells, the value of maximum cell counter will be displayed as the answer. This program can be classified under DFS or depth first search algorithm. Let's implement this logic in Python language. For that, we will be using the HackerRank platform. This is the problem statement we will be solving. The link to this page is provided in the video description. Let's open the code editor in full screen mode. Change the language to Python 3. There is already some code provided in the editor. We just have to complete this function. As an argument to the function, we do have the input matrix here named grid. Let's start coding. First, we will initialize a variable max cell counter.
I'm gonna search how to create a matrix with NumPy. I think there is a way to create it in one line only. Whatever.
With value 0. Now, we will add 2 for loops to iterate through the list grid. In Python, a matrix will be represented as a list which contains lists as its elements. In this case, our matrix grid is a list which contains each row of a matrix as its element. To get the number of rows, we will check the length of grid. To get the number of columns, we will check the length of the first element of grid. While iterating through each cell, we will check whether the current cell contains the value 1. If yes, we will calculate the number of cells having value 1, including its neighbor. For this purpose, we will write a separate function count region cells. This function will take the grid, current row and current column as the arguments, and this function will return the total region cell count. The result will be stored in a variable region cell count. At this point, we will check whether the current region cell count is greater than the existing maximum cell count. That is, the maximum value among the current region cell count and existing maximum cell count will be the new maximum value. This value will be returned as the result of the main function. Now let's write the definition for the function count region cells. One in row plus 2 will
Now that we
I'm gonna take a break from this and do this thing here. Just close this. There's too much reflection on the window. Oh, I might have to sign up again. Yeah. print down there. I think there are flags for recursive. Something like that, but I'm not sure. And cut the. Oh, which one? It's something. I think is there. Yeah. Time. Let's remove there. I think I'm gonna test. I don't remember this one. Yeah. I'm gonna test to see if I pass this. This one I don't remember if it's who am I or finger user. I think it's who am I actually. Yeah, this one I don't remember. I don't know. Oh, sprint directory here as well. Oh, well, T. Whatever. I don't think I'm gonna worry about solving these problems, actually. I think I'm gonna focus more on, because otherwise I'm not gonna be able to do them. It's just not that interesting to me. I'm not invested in this enough to spend time thinking about it. That's what I feel like what's happening here is that I can think about different ways or different things that I can do, but I just don't care enough to do them. So my natural inclination is obviously to be lazy about it and not build the problem and then try. I'm trying to think about if I can find some application or something that I can try to build that involves graphs that is not gonna take too long, so I don't get caught up. I think what I'm gonna do is actually what I was talking about before, where I'm gonna make a list of the most known graphs and methods, the most well-known algorithms and methods for graphs, and then I'm gonna study them instead of doing the problems. I think that's probably more effective for my way, my style of learning, I think. And I also need to study recursion as well. I think that's one thing that is stopping me from solving this fast. Because it's really hard for me to think about the recursion. Yeah, that's what I'm gonna do, I think. So first I'm gonna see if I can find if I can go over all of these tasks here because I want to finish this. I'm gonna try to go as fast as possible. As soon as I'm able to pass, I'm gonna go to the next one. After I'm done with this, I'm gonna come back and then I'm gonna study. I'm gonna search for well-known graph algorithms. Then I'm gonna see. I'm gonna try to extract the core principles that they use, and then after I extract the core principles, I'm gonna study them and see if I can. I'm not gonna worry about the problems here actually. Maybe I should change the title of the thing, but and then after I do that, then I'm gonna search for what are the applications. When did these things show up? The other thing that I have to do is study the Lighthouse client as well. I wanna do that as well, so I might do that as well. Yeah. I think it's touch. Yeah. Yeah. Good idea. Oh, so the file don't need the R flag because it's not recursive. I think the slash R is for recursive. Mm. Let's move. Oh, it's hat. I tell you far. Hmm. I think this is. Oh, I'm confusing the two of them. I also confuse that one all the time. I'm gonna try to do the task already. Fuck. I forgot this one, but I know it was link 1 file 1 at the end there. Just don't remember the whole command. Yeah, I'm just gonna skip this. This I think is cat file. Oh fuck. I got the other one wrong. Because this one is the tail, I think. Or tail file. I don't know this. I have no idea as well. I'm probably gonna fail this one. I'm gonna try again or pass. This is LN as file 1, link 1. Day1 file. I think I'm gonna train a little bit more because there is a couple of them that I'm not getting it. Like this one. I know that I think it's not head file or tail file because it's the first. Maybe this is the cats, but I think it's not the cats one. Yeah, more file. More file. This one I think is the cat. Oh, maybe not. Tail F file. Maybe this is the cat one. Okay. Put standard output in true file. It's ln l link 1 file 1. Or is as file 1 link 1. Oh yes, it is this. I think this is move file or something like that. No. This is the cat one. I wish I could skip all the commands, the ones that I don't know. This is probably the move. More file. Yeah. I think I'm gonna try again. Yeah, there we go. Nice. Next one. I'm gonna take a break. I'm trying to think what I should do next, if I really should study or should keep trying to do these problems. Because it might be the case that I'm just trying to rationalize because it's harder for me because I'm not good at these problems yet. So I'm trying to do something else, but it also might be the case that that is just not the way that I learn the best way. It kind of reminds me of formal education, which I think is garbage because it has nothing to do with real life. It's just a problem that you're not gonna gain anything out of it, and there isn't enough investment to do the problem. That's the thing for me. It's not that interesting to me. I guess I can try the other approach because so far I only tried to do lead code problems to learn data structure and algorithms. I haven't tried to search for the algorithms instead and search for real problems and then trying to see the solutions to the problems and seeing maybe if I can build something that involves that, which I think is gonna be the problem with that is that it might be too hard to start, or it might be too hard or too easy because I'm gonna have the solutions. Maybe I can do something with Network X now that I think about it, some visualization stuff like I did in the past, and then can try to implement. Yeah, I think that's a good idea actually. I can try to implement algorithms that I find into the visualization thing with Network X. That might be a good idea. Oh, the other thing that I forgot to talk about is that this stuff broke again in the middle of it. It corrupted the database because of some virus or some stuff like that. And then I had to start from scratch again to get the data, which is quite annoying. That's one of the reasons why I want to see how the software works, to see if I can find something in the source code that allows me to sync faster. Because every time that there is something wrong with the database, you have to delete everything and start from the beginning, which is annoying. I wish there was a way to just delete the files that were corrupted and then only sync from that point forward, and that's um, why I want to see if there's a way, if I can explore the source code to figure out how it works. And it's also gonna help me to, whenever this finishes syncing and then this starts syncing, if I understand this, how the source code works more, then it's gonna be easier to know how to interact with the nodes as well. That's the other point. Yeah, but let me think about it. I'm gonna continue to do this. I'm gonna take a small break, to go to the bathroom. And I'm gonna finish this stuff, continue to do this stuff and finish this. And then after that, I don't think I'm gonna do lead codes. I'm gonna pause this and I'm gonna search for the graphs and see for the algorithms and see if, and try to think about something I can do. Well, the other thing that I thinking about now is that I've heard from Andrew Neiman podcast that if you are in environments with high ceilings, it puts you more into a mode where you have expensive ideas and it's better for big type of thinking, for more of the general picture. And if you want to think more analytic and more in detail, a smaller ceiling works better. So the tip that he gives to optimize for each one is to, whenever you're gonna do some analytical thinking, you put a cap on, because it kind of simulates a small ceiling, which I think is quite interesting. You know, I think I'm gonna try that. I just remember that now. So I think what I'm gonna do first is search for the algorithms. Then I'm gonna think about something I can do with Network X or visualization that I think is interesting, and or maybe I'll look into the applications of these algorithms. and see if I can implement some of them with the visualization. I think that's going to be a better and more engaging way of learning how to do them, because then I'm going to be more invested into solving the problem. I'll be right back. It has to be something related to blockchains. Maybe I'll do something with Solana or Cardano, something like that. Trying to think about what I can do. I think for graphs is gonna be easier, but for trees it's kind of hard to think about. I can do I can change the poker project that I was doing and implement, because it is kind of, I am implementing a tree structure in that project, but I want to take more time now to focus on blockchain instead. And blockchain, obviously, I can do something with Merkle tree, because, or Trias tree, whatever you say that, because it is a Merkle Patricia tree, this structure. But I want to become better at understanding trees as well. Yeah, I have to think about. It's gonna be easier, I think, after I search for the algorithms and their applications. Should think about it, I think. I'm gonna put some music for myself here while I do this stuff. Hmm. Fuck. I think I'm gonna try to do the test already. I'm never sure about this one. And this one I was confused with who am I think. I'm not sure if it's who am I or W. And there we go, nice. Next one. And we'll do 2 more and then go back to what I was doing. Oh fuck. Forgot the after. Oh, it's sad. Control H. Behind curves. I think I'm gonna try to pass because there's a lot of tests that are a lot of different things that are repeated from the previous one. Fuck. I have no idea. Just Control R, something like that. Or whatever. No idea as well about this one. Should dance. Or maybe this is down. Is either down or up, I think. No idea again. I have no idea. Okay. Oh, erase is control U. And this control E. And so I got these ones twisted as well, which doesn't matter that much. Yeah. I want to move on to the next. I'm gonna do just this one more and then I'll go back to searching for algorithms. Control H. I have no idea. I think it's this in new. FG foreground. Not that hard actually. It's easier than the Vim ones, I think. Oh, current command. I don't remember. Okay. Which one? I think I'm gonna try again. Try to do the test. There's a bunch of them that are repeated, so I think I'm gonna pass. This is down. Yeah, last day of foreground is FG. Not sure if this is up or something else. Previous command. I think is up. Alt is Control C, I think. Recent commands. Control R. J. Control A, I think. Beginning of the line. Control E is dance. CMD. First is have. Didn't I just do this one? Maybe I got the previous one incorrect or wrong. Oh, this one was Control Z. I was confused this one. Fuck. I have no idea about this one. Display all processes. I don't remember. Oh, top. Control Z. Yeah, Q9, 5. Yeah, so the only difference between this one and this one is the Q here, which I don't understand. I guess this one closes the thing, but this one terminates. But what's the difference? Not really sure. Yeah, I'm gonna go back to studying this and then I'll finish that later. I think I'm gonna watch these videos here and then I'm gonna search for algorithms for graphs and trees, and then there are applications, and then I'll think about what I can do.
Basics of the data structure of a 2D array, let's talk about traversing through it
I think I'm gonna spend 50 minutes and then I'll take a break again.
using breadth first search and depth first search. With this one, we're actually going to start with depth first search first. Depth first search in a 2D array is very similar to depth first search inside of a binary tree. With a binary tree, we usually start from the root, whereas with a 2D array, you can technically start from any element inside of the structure. Most of the time, though, as I mentioned, we're going to start in the top left corner at row 0, column 0. Think back to depth first search in binary trees. At any given tree node, you could explore one of two directions, either the left child or the right child. Here, at any given element in our 2D array, we can explore one of four directions, up, right, down, or left. So just like depth first search with a binary tree, where you explore as far down one branch as you could, being the left branch or the right branch, here we want to explore as far in one of the four directions as we can until we either hit the outer wall of the 2D array or going back to some element that we've already explored. At that point, then we're going to change directions. And we're going to walk through this very extensively so you understand what decision gets made at every single element before we proceed to the next appropriate element and take the value. So here, starting at 0, 0, we take the 1. So here we're going to usually move in the same pattern of directions, meaning the choices that we have are going to follow either up, right, down, left, or some combination of your choice. Most of the time, it's going to be up, then right, then down, then left. So here, we're going to first try and go up, but there's a wall, so we don't want to go that way. Next, we're going to then try right, and here we're going to proceed to the next element, taking and increasing column by 1, and we're going to take the value out here, which is 2. Now we're going to try once again, go up, there's no value. We're going to go right, take that value, which is 3, and you'll see at the bottom array here, we've been accumulating the values that we explore. Once again, we're going to go up, there's nothing, so we're going to go right. Then once again, go up, there's nothing, go right. And now when we try to go up, there's nothing, go right, there's nothing, and then we're going to go down. Here, when we try and go up again, we're going to notice that we've already got the 5. We've explored that cell inside of this 2D array already. There's no need to go back up. So we're going to try and go right, but there's a wall, so there's nothing, and then we're going to go down. Here, we're going to take the value, and once again, going up, we've already explored. Going right, there's nothing, go down, take the 20. From 20, we're going to go up and see that we've already taken the 15, so we don't want to go that way. Go right, there's nothing there. Go down, there's nothing there, so we're going to go left, and we're going to take the 19. Here, we're going to retry our directions again. The first is going up, but we can take that value. We haven't been there yet, so we're going to take 14. Then we're going to go up again, take 9, because that's perfectly fine. And then when we try and go up again, here we're going to see that we've already taken the 4, so there's nothing there. We try to go right, we've already taken the 10, there's no need to go that way. We're going to go down, we've already taken the 14, we don't need to go there, so then we're going to go left and take the 8. Now we're going to try once again. Go up, there's no need, go right, there's no need, go down. So we're gonna take 13. 13 is a new element, so we reset our directions. So we start by going up, but we've already taken the 8. Go right, we've already taken the 14. We go down, that's a new element, we take the 18.
I think I'm
From
gonna
here,
search for how the cache works in Python because I know the decorator. Because I understand that it caches, but I don't understand how does it do that.
once again, we reset, we try and go up. There's no need, we're taking the 13. Go right, we've already taken the 19. Go down, there's nothing there. Go left then, take the 17. Reset our directions, we go up, having explored it, take the 12. We go up again, having explored it, take the 7. Go up, we can't because we've already explored the 2, so we don't need it. Go right, we've already explored the 8, we don't need it. Go down, we've already explored the 12, we don't need it. So we go left and we take the 6. 6 is a new element, so we reset our directions, we try and go up, but we've already explored the 1, so we don't need to. We go right, we've already explored the 7, we don't need to.
Well, the other thing that I remember seeing after I closed the stream last time I was working on the poker project is that you can use a macro in Rust called clone, I think. You put derive and then clone, and that macro allows you to copy complex structures. It implements a implement for every structure that returns self, and once you do that, you're able to copy. So that's one possible solution to the problems I was having there with the project. But I remember last time I tested, it was also working as well. So I didn't try to output the hands into a file, but it was working. It was passing everything to the hand vector, to the final hand vector. So it seemed that everything was working since last time I saw it. But then if it doesn't work, I can implement that derive clone, and it's probably gonna work that way.
So we go down, which is new, we take the 11. Here we reset our directions again, we go up, we've already taken the 6, we don't need to. We go right, we've already taken the 12, we don't need to. We go down, and we take the 16. So this is very thorough, exploring how depth first search works inside of this 2D array. Just like depth first search in a binary tree, depth first search inside of this 2D array is going to be using a recursive method. You can do it iteratively, and if you do it iteratively, you'll use a stack instead, but most of the time, the recursive nature of depth first search lends itself to better solutions and thinking about how to get the answer to these 2D array questions that might use depth first search. Recursion by itself is easier for us to reason about than the iterative solution, and most of the time, no interviewer is going to expect you to do the iterative method. It's way too much of an optimal solution to implement in such a short time frame. So what we're going to explore in the next video is the depth first search code implementation inside of these 2D arrays. Before we move on, though, I do want to challenge you to think about how that code might be structured. You don't have to code it out, but by all means, if you want to, try. The main thing I want you to focus on is just the components that's going to go into this depth first search algorithm that we're going to write. I've already given you some hints. The first one is that it's going to be recursive in nature. So I want you to think about what elements and what arguments you're going to be passing through to these recursive function calls. The other thing is you need to figure out a way to keep track of which elements in the 2D array we've already explored. You also want to make sure that with 2D arrays, these elements don't necessarily have to be unique. We can have duplicate elements inside of the 2D array. So this thing that you're using to keep track of the values needs to be able to keep that into account. It cannot be by the value inside of the element of the 2D array. The other thing to note as well is that your lookup time for this structure that you're using to keep track of the elements that we've seen should perform at O of 1 time. If you use some kind of scaling performance version of lookup to figure out what element we've already seen already, that is drastically going to ruin this performance of our depth first search. So these are the main things I want you to think about. And in the next video, I will show you, and you can compare your solution to mine.
It doesn't teach anything.
Hi thinkers, welcome to the data structures in Python course on thinkexacademy.com. In this tutorial, we're going to study the DFS, which is the depth first search algorithm in graph data structure. We have previously covered the depth first search and we have also implemented it in Python. And here we're going to do the same. And basically, there are two approaches to implement the depth first search. The first approach is the recursive approach, and the second approach is using the stack data structure. In this video, we're going to focus on the recursive part only. So here you can see I have a graph data structure A, B, C, D, E. And here you can see I have used a similar representation of this graph using a dictionary data structure. So here we have graph equals to, and you can see this is a dictionary with keys and values. Now value is a whole set of all the adjacent nodes which are connected. So here you can see if I have a key which is A node, so A is connected to B, C, and D. So they are the values of this key. So you can see here A is connected to B, C, and D. Now B is connected to A and E. Now B is connected to A is already covered here, so we are not going to rewrite it here. So B is E is the adjacent node of B, so that's the representation of it. Now we have finally C, D, and E in similar way. You can see D is connected to A and C, and we have already covered that before because you can see that C is connected to D and D is connected to C is same. So we're not going to rewrite it. So to the left part of the tree, right? So this is the left part. So now in the left part, if I move to this node here, so I'm visiting it now because the end of the understand DFS more clear. The second we're going to visit E, the recursive approach, which we will use in this tutorial, right? So an array which will contain and hold all the elements or the nodes that we have already visited, whether the root is inside of the visited set or not, right? So I will write if root not in visited, right? Print the root element which is A, and then I'm going to simply, so the neighbor will go from B, then in the next iteration it will be C, and then in the, and now again we will you can see now node, D node, and E node. When it will be able to run all of this, it is now going to backtrack and it will visit all the remaining nodes as we have seen inside of this, right? So this is basic working of this whole algorithm. In recursive approach, it's simple because what we are doing is whenever we are visiting a neighboring node, right, same path again and again, algorithm works. Now make sure to understand how this recursion is.
So today we are now going to write the DFS code in Python. So you already know how the algorithm works. Now let's write the code. It's similar to the breadth first search, but this time we are going to be using a stack. So I'm going to start writing the code now. So it's going to be DFS, AL, and yeah. So we need two things. One, the visited array and a stack. Okay, so to implement this stack, we're also going to use a list or a set. So I'm going to say stack is equal to a new stack, and I'm going to say visited is equal to an empty list as well. Now, the first item we are going to put into the stack is the root. So I'm going to put the root item, which is G, onto the stack. So this is standard, you have to put this root item right there. Okay, so let me make some room here, and we are now going to look through this stack, and for each item, so once we put something in the stack, okay, we are going to now iterate through the stack for each item in the stack. If it has any unvisited child, we are going to add those unvisited children to the stack. So I'm going to write out the code. I'm going to say for actually while stack is not none. Actually, you can just write it in short form while stack. So while there's something in the stack, we're going to grab the first item on the stack. So I'm going to say node is equal to stack.pop. So this is going to retrieve the item, the first item from the stack, and we are now going to add it to the visited array, provided it has not already been visited. So I'm going to say if node, and after adding it, we are now going to also add the children of this node to the stack. So I'm going to say, yeah, so the children of this node can be added to the stack using a loop that loops through this node. So the adjacency list of this stack.append x and al for x and al node stack z. So basically it's going down. Once it starts, it goes down, and it comes back up here, goes down, comes back here, goes this way, and it goes all the way out this list. So I'm going to just uncomment this. So this is also a depth first search.
Hello and welcome to the channel. Today I'm going to go over a hard algorithm problem called longest increasing path in a matrix. This problem has been asked at a bunch of tech companies, mainly Google, but also at all of the FANG companies. This is definitely a hard problem because it involves knowing how to write recursive algorithms, the DFS algorithm, and understanding how to use and implement.
I'll watch a couple of videos about recursion first and the caching. Then I'll watch the other ones about the depth first search.
Developing recursive solutions to the problems that you're trying to solve isn't a skill that comes naturally to many people, and I know this because it didn't come naturally to me. But using one cool trick that we're going to reveal in today's lesson will hopefully give you a light bulb moment the same way that it did me in reframing the way that you think about these problems and giving you a much more approachable way to go about solving recursive challenges. So let's get started by thinking about recursive structures and what we mean by this. Well, we're talking about in this sequence the simplest recursive data structure we can imagine, which is a singly linked list. And we can imagine a singly linked list where each of our node objects has some values associated with them. So say 110 and 210, just some numbers out of the blue, and then our lists are terminated with none, not node, none. Each of these are node objects. So I mean, label these as my haystack. We're going to be implementing a search algorithm here, and we're going to be searching in a haystack. This will be our haystack of node objects. Right, this is our linked list. Okay, and if we're going to get some practice thinking about a recursive algorithm, we need some problem to solve. So we're going to be asking, does this list include 210? Does any node in this list include a value such as 210 in it, right? And if we want to come up with a recursive solution to this problem, we're going to need to think a little bit differently than we would if we were thinking imperatively about this. And so before we get into a recursive solution, let's think about if we were trying to think of an imperative solution to this problem. And when I use the word imperative, I tend to mean loops, right? And this is what it classically means. So imperative, we're thinking about looping through a problem. So we would start at the front, and for each node in my list, we're checking to see whether or not it's what I'm looking for, and then we're done with it, right? So in an imperative solution to a problem, often we think about like, okay, we're going to start at the very front, and we're going to keep looping until we reach the end. And if in the middle of that process we find what we're looking for, we'll go ahead and return, we get all the way to the end, and then at the very last step would be, well, we didn't find it, right? And so this is a very natural way of describing and coming up with a solution to a problem, often for many people. With recursion, the trick that we're going to learn is to actually flip the script on that process entirely and try and think about, well, how do we solve this from the back of our problem or from the end of our problem, from the simplest type of problem we can imagine and work our way back out of it. So let's imagine what this might look like. First, our goal is to have a function that has a signature that looks something like this. Includes is going to be the name of our function, and we're going to have two parameters, right? A haystack, that's what we're searching through, that's going to be a list of nodes, and a needle, right? So we're looking for a needle in a haystack, and this should return a Boolean, right? True, false. And what we're writing out here is very much just pseudocode, thinking about this problem in a very abstract and wavy sense, right? So what is the simplest problem we could solve here? Like, what is the easiest haystack we can imagine just to work through to know whether or not we found the needle that we're looking for? Well, the empty list, right? When there's nothing to search, we know that sure enough, there's no, we haven't found the needle, right? So we can imagine one case that should be pretty easy to solve. So it includes, and if we're looking for, our list is none, or the empty list, and we're looking for a needle like 210, right? We would expect that to result in a false value, right? We haven't found 210, and 210 is not included in the empty list none, right? And so we would think of this as a base case. And the strategy that we're learning here is to start by thinking about your base cases. Start with the simplest problems you can imagine. What are the ways that you know that you sort of completed your job with the least amount of work possible? It's a very lazy approach to thinking about solving a problem, right? Well, yeah, of course, like this will be easy to implement. If you give me none, I'm going to give you back false, and my job is done. Well, what's the next most challenging list we can imagine solving, or next most challenging haystack we can imagine? Let's say we're includes. And what about a list where the haystack that we're given is just a head node of some list is going to be, say, the node 210. And I'm just going to draw an arrow to nothing. We don't know what comes after this based on one invocation of this function. Right? We're just given one node at a time, and we're going to be trying to think about one node at a time. That's going to be one of the key strategies involved in this process. And we're looking for 210. And this feels like a pretty easy solution too, right? Like, sure, you give me 210 as the first node in my haystack, and I'm going to give you back true, like, because that's what you're looking for. I know that we found it, right? So this would be another base case, right? We know exactly what to return. We can completely solve the problem that we were trying to solve at this point. There's not, I've seen enough, right? We don't have any more work to do. Well, what's the next most challenging thing we can do? So notice we're working our way from the simplest problem that we could solve to a slightly more challenging. And the key strategy we're going to employ here is, well, if we don't know how to solve the problem with the current position we're at in this list, we're going to do what we need to do with the current node and then leave the rest to recursion. We're going to say, recursive function calls, that's your problem to go worry about, right? And so if we imagine, okay, well, what about includes? And we're going to use, I'm just going to reference haystack as the variable that references, the node 110 haystack, and 210 is what we're looking for. And what is this going to result in? Well, we're going to be lazy here. We're going to say, we can't solve this, but we know that, the node you're looking for, the value you're looking for isn't the top of the haystack, isn't the head of the haystack. So, go do this again, but on the rest of the list, right? Go leave the rest of the recursion. Right? We're going to be lazy here and say, okay, well, maybe check the next list using the exact same the next value in the list using the exact same process. So includes, and then haystack.next. And I'm going to run out of space here. So I'm just going to wrap around and say haystack.next and 210, right? So check the rest of the list for the value 210. And this is our recursive case, right? So this is our recursive case. And if the next value is going to be 210, then we would return true. If it's going to be none, then we know we've reached the end of our list and our job is complete. Otherwise, if it's neither of those cases, if it's neither of our base cases, then we're going to try again on the next node, right? But notice we're sort of working our way from the back of the problem, from the simplest case possible towards the recursive case that's going to move through each item recursively. So now we've got this general strategy down. Let's try implementing this in some code. Right, so in VS Code, I've got the starting point, some of the starting code from our current exercise 6, where we're implementing some linked list algorithms. And I'm going to continue on in this file. And I would encourage you to go ahead and set up exercise 6 to be sure you're ready to start on it. And you can follow along with the video once you're there. If you otherwise want to just jot down this code in a scratch file somewhere, that would be totally fine too. There's no more code than this for this particular exercise. So pause the video here and be ready to continue coding and resume once you're done. So let's take a look at what you're seeing here. This class node is a node in a linked list. It has two attributes, a data attribute that's storing the number of a node, and then next, which is importantly an optional next node, meaning it's either going to be a node or it's going to be none when we reach the end of our list. We've got a constructor that we talked to before, and then there's this magic method that's special because of these double underscores named repr. And we're going to talk explicitly about repr in a video coming up, right? But for now, I'm going to shorthand, leave it to the documentation to say this produces a string representation of a linked list, and we can get a feel for this in just a moment once we are testing our data out. But basically, it's going to automatically create a string representation of a linked list. So it's like 110 and an arrow, and then 210 and an arrow, and then none is what we would expect given our previous example. So let's go ahead and set up a skeleton for the function we're trying to implement. So def includes, and we have our haystack, which is a parameter. And what is the type of haystack going to be? Well, we need to be able to support an empty list, but we also need to be able to support a node or some start of node, some head. So we can use optional node as the parameter type, and we need the thing that we're looking for. That's going to be our needle, which is an integer, and it's a function that returns a Boolean value. And for documentation purposes, we might just write, okay, return, or let's just form this in terms of a question, because this is what we call a predicate. Is needle included? Is needle in the haystack? Right? Okay, well, we've previously applied our new strategy and technique for solving a recursive function. So let's go take a look at what we had. We had a base case where if haystack is none, we're going to return false. Right? So let's go try and add that case to our code. So if haystack is none, we've reached the end of our list, so we can return false. Right? Our job is done. There's no more for us to see here. You didn't find what you were looking for in this list. Else, what we can do, and actually let's just do this as an elif haystack.data is equal to needle. Then what are we going to do? Well, this is the case where we found the needle in the haystack, right? And we're going to return true. Right? Finally, we have an else clause, and this is going to be our recursive case. We covered our two base cases, and we can remind ourselves of those really quickly. So we've covered the case where we found what we're looking for. That's the second base case. We found the case where we reached the end. We didn't find what we were looking for. That's the first base case. And now we're saying in the recursive case, well, we don't know. Let's leave the rest of the problem to the beauty of recursion to figure it out and process the rest of the list recursively by applying the same process recursively. Right? So let's try and express that in a little bit of Python code. Otherwise, we're going to return includes haystack.next, so process the next of the list, and with the same needle. Right? And that's a pretty straight translation from trying to conceptualize a solution to this problem by working our way out from the back, by thinking about something a little bit simpler to test whether or not it works. But I had too many parentheses when I tried to the haystack when the first recursive. That is the important. This is actually great to recognize when I.
Hello and welcome. Today I wanted to share with you what, in my opinion, is the single most useful decorator in Python. Taking a look at the code that's already written here, first we have a function which computes the nth Fibonacci number, and it does so in a recursive fashion, so it's extremely inefficient. Next, in our main function, we have just a loop going through 400 numbers, just printing out the number and the ith Fibonacci number. And then at the end, we print done. Now, if I were to actually run this code, you would see that while the first few go very quickly, it starts grinding to a halt around 31, 32, 33, and essentially each number after that takes twice as long as the number before it. And this is because of the bad implementation of the Fibonacci function that we've given here. The main problem with this implementation is that when I compute fib of n-1, well, part of that computation is to compute fib of n-2. So I'm doing a lot of repeated work here. Every level down, I'm going to be repeating work that has already been done and then just was thrown away in a different function call. An easy way to fix this is just by remembering values that have already been computed. And that's what the decorator does. So my favorite decorator in Python is the cache decorator from the functools library. So functools is built in, so you don't have to install anything. And then you just hit your Fibonacci function with cache, and now let's go ahead and try running it again. You see it goes through all 400 of them immediately. And the reason for that was that even though we have this very inefficient definition, what cache does is it just remembers all of the values of the function that it's computed before. So if you compute fib of 398, then when I compute fib of 399, it looks up fib of 398 and 397, and it says, oh, I've already computed both of those things. Instead of recomputing them using this recursive definition, it will just use the value that it's remembered from the previous time that you've run the function. So I find this to be extremely useful because it allows you to avoid repeated computations. There's also a variant of cache called LRU cache. LRU stands for least recently used, and it does essentially the same thing, but instead of storing all previous values of the function that you called it with, it only stores a certain number of them. So let's just replace this with an LRU cache and give it a max size of, say, 5. This means that it's just going to store the 5 most recent values of the function that I called. Now, if I'm just running up values of the function in a for loop like this, then that's plenty just to do this. So still, if I run the function, it completes just as fast as before. And this way, I'm only using a little bit more memory, but it's a huge speed up compared to when there was no cache at all. So I found myself using cache or LRU cache in a lot of different projects, just anywhere where I can see myself accidentally repeating computations that might take a long time. That's a great place to just throw it in, a cache or an LRU cache. You don't have to do any other work, and it can provide a lot of speed up if you know the right place to use it.
Hi, my name is Simon, and in this tutorial we're going to have a look at using caching decorators to speed up our applications. Now, decorators in general are a fantastic concept in Python, and they enable very interesting features for decorators in Python. Before proceeding here, I'll post the link in the description. Functions will do a lot of heavy and time-consuming calculations. Now, every just come into play. Let's we'll have
It's just going to be the same
so
thing.
we'll do some more calculations, multiply
the
them.
other.
But we retrieve it from our cache, which will speed up things a lot because no calculation is required. So let's see how our caching decorator works under the hood. So here we initialize our cache decorator function and pass in the function to execute. Next we create a dictionary in which we can store our caches in. Inside our wrapper function we define our signature, which is a variable result, and its value is the return value of invoking our function that we have passed into our decorator function, where we do a tuple unpacking to get in all the needed arguments. Now this is useful to not limit ourselves on a fixed number of arguments, because if we have a quick look at the add and multiply functions at the bottom, we see that they have a different length of arguments that we have to pass in. Using a tuple unpacking in here, we guarantee that all needed arguments are passed into our function to invoke. So after calculating the result, we use another logging message that we are about to store the result in our cache. So we use our cache dictionary and use our signature as key and store the result as a value. Now due to the fact that we use this function as a decorator, the cache won't get out of scope and we can keep all the previously calculated results in memory. Next we return the result, which is either coming from our calculation or from our cache, and return the wrap function. Perfect. This enables us now using cache data whenever we have already calculated something using a function and given arguments. This will dramatically speed up our applications because we don't need to calculate the same thing over and over again. I hope this illustrated to you the power of decorators. Now there are a lot of more
Maybe
situations where
what I can search for is how to find fractal patterns in data. That might be an interesting thing to search for, and something that I'm interested in, and it's probably going to involve recursion. So how to get a data set and then find a fractal in the data set, or approximation of a fractal. Yeah, that might be too difficult. It's probably going to involve machine learning as well to correct or to fit the data set. It's probably machine learning.
Recursion is basically when a function is able to call itself. So imagine we have a basic function like this.
It's all about taking a problem and solving it using simpler versions of the problem. So the first step in solving a recursive problem requires you to ask yourself, what's the simplest possible input for the function? Here, the simplest possible case is n equals 0, where we know that the result should also be 0. The simplest case often translates itself into a base case for our recursive problem. The base case of a recursive function is the only input where we provide an explicit answer. All other solutions to the problem will build on the base case. The second key step to solving recursive problems is trying examples and visualizing how the inputs and outputs of these functions interact. In this problem, one fun way to visualize things is to treat our sum as building a triangle with the base as the input value. That way, our sum is the total number of individual blocks in this triangle. You can try as many examples as you want. Once we have a set of examples, we now want to move to the third step, which involves relating larger examples to smaller examples. Take a second to see if you see any relationships between the cases here that pop out to you. Put in more specific terms with these examples, ask yourself, hey, if I was given the answer for the n equals 4 case, could I solve the n equals 5 case? If I was given the answer to the n equals 3 case, could I solve the n equals 4 case? One interesting relationship that you may have noticed is that if we know the answer to the n equals 4 case, all we need to do is add 5 to this answer to get the solution to our n equals 5 case. And similarly, if we know the answer to the n equals 3 case, we can get the answer to the n equals 4 case by adding 4. And it's not too hard to convince yourself that this should be true in general, but if necessary, feel free to try some larger cases to verify. This now brings us to the fourth key step, which is to generalize this pattern. Let's say we want to figure out the sum for the input n equals k. We can find the sum by first taking the sum up to n equals k minus 1, and then all we have to do is add k to this value. Once we generalize the pattern, the last step now involves writing code by combining this recursive pattern with the base case. This actually turns out to be not too hard since the code almost writes itself from our base cases and recursive pattern. Let's dig a little bit deeper to see how this really works for a particular input. Let's say we run this function for input n equals 5. What actually ends up happening? Well, we go through the initial function and then hit a recursive case, which adds 5 to the result of calling our sum function on the input 4. So we know that this should theoretically give us the value 10, but technically, this function hasn't been evaluated yet. What actually ends up happening is we have to go back into our function and repeat the process. We hit the recursive case again, which then causes us to now add 4 to the value of sum called on 3, which once again kicks off the same process as before. Let's take a moment to see how this unravels. This continues until we hit the base case, which then is used to solve the sum function called on n equals 1, which then solves the sum function called on n equals 2, and so on and so forth, until we eventually build up the solution for our original n equals 5 case. It's always okay to take some time to unravel the recursion to ensure that things work, but as you get more experience solving these type of problems, there's a concept called the recursive leap of faith that I would like you to think about. The recursive leap of faith makes solving recursive problems much faster. It's all about assuming that easier versions of the problem will be correct. In this particular problem, the recursive leap of faith would say that if I wanted to solve sum called on n equals 5, let me just assume that sum on n equals 4 is going to work, and then if I add 5 to that, sum called on n equals 5 will also be correct. Don't worry if you're a little hesitant to believe in the recursive leap of faith, but it is a useful problem solving trick that helps in more complex recursive problems. Let's now explore a more involved recursive problem. Here's the problem. Write a function that takes two inputs n and m and outputs the number of unique paths.
So here's what I'm thinking. I'm thinking about searching this. And maybe I'll go back and try to solve this problem. I think this problem is about trying to figure out how to find the boundaries. What I'm thinking about is that every graph problem is going to be roughly the same way. And what happens is you have the recursive calls, and the if-else statements inside of the recursive call are the patterns you're searching for in the graph. So in a way, the structure of if-else statements represent the geometrical structure inside of a graph, and you can represent anything inside of a matrix. A Cartesian matrix can represent functions and fractals. So what I'm thinking about is maybe that's a more interesting way to learn, because the question that popped up in my mind is, if I have a matrix or a Cartesian plane or something like that, a matrix with coordinates, how can I find a fractal pattern inside of that matrix? And what is the difference between patterns inside of the matrix? And it's probably correlated with functions as well, because now that I think about it, a function is just you can think about a function as a sequence of zeros and ones for checking if some value is inside of the function or not, inside of an infinite matrix that represents the Cartesian coordinates. So there's also probably a correlation there. It has to be, because you're also using functions here. So I think the question is, if given a matrix, how can I find the patterns, and what is the difference between the patterns? And then can I create an algorithm or a way of approaching this? Because I've noticed so far, the stuff that I'm doing in Python, I always do the same stuff, but I'm not used to doing recursive things or working with graphs. But usually what I do is loop through arrays, and then I put logic inside of the arrays, and the problems are always the same. I think that's very common in everything you do. You have the first principles, which are the laws of physics that are in everything pretty much, and then you have the nuances from that, which change every time. So each problem is going to be a combination, a distribution of those. And you're going to have the first principles, which are going to remain the same, and then which are the fundamentals, and you have the nuances, which are the things that change. In graphs, I think that the principles are the depth first search or these recursive calls, and then what changes is the structure of if-else statements that represent the geometrical structure you're trying to withdraw from the graph. Or, yeah, because the geometrical structure can be viewed as the path as well to whatever you're doing. So the challenge is always going to be how to find the geometrical structure that solves whatever the question is asking for, I think. inside of the recursive. And what I'm lacking here is understanding, not understanding, because I think I understand really well already. The problem in this is why it's difficult for me to search these things, because I know what they're gonna talk about, but what I'm trying to extract is when I see the problem, how I go about thinking about the problem and the solution. That's the problem that I have. Because with lists it's very easy. You just think it's very intuitive to think about it, looping through a list or using objects inside of the list to get values. But with graphs, to think about the simple scenario, to think about the solution, let's say, and work backwards, it's very hard for me. What they talk about there, where you have to think about the simplest case and then go backwards, it doesn't make a lot of sense to me. It's not very intuitive. And I'm trying to think about how can I study in a way that I'm gonna fix that or create a meta algorithm, let's say. So a sequence of steps that allow me to gain more intuition about how to solve these problems. So I think I'm gonna try to do that. I think that's more interesting. The only thing that I have to think about is, well, the first thing that I'm gonna do is search for the common graph problems, common graph algorithms, and then try to see what's common between them. Then I'm gonna try to find fractal patterns inside of a graph. Create an algorithm that finds different fractal patterns inside of a graph. That's probably more interesting. And as I watch these videos, I'm gonna think about how to connect this with the blockchain. The problem, the unfortunate thing now is that I don't have the data yet, so there's not much I can do without the data. But maybe there's something that I can think about that doesn't require the data, that involves blockchain, so I can connect both of these things. Oh, maybe one thing I can do is try to reconstruct a blockchain from scratch and do it in a fractal. It is gonna be fractal. That's the thing. And it's gonna follow the market economy, I think. The patterns of transactions of a blockchain. Because it is probably a Pareto distribution. Because it's built on top of market economy. But maybe that's too hard as well. To recreate an EVM, I think that's gonna be too much. It's gonna take too long, and it might make me deviate from the original goal, which is to become better at dealing with graphs and trees.
Left corner to the bottom right corner of an n by
I'll
n
be right back.
One key constraint is that you can only move down or right one unit at a time. Before we apply our 5 steps, let's first familiarize ourselves with a few inputs and outputs for this function. Here's what happens when n equals 2 and m is equal to 4. We end up with exactly 4 paths. And here's another example with n equals 3 and n equals 3. We end up with 6 unique paths. Alright, let's begin. Let's play around with some simple inputs and see what happens. The simplest possible reasonable input to this function is a 1x1 grid, where we end up with exactly 1 path. If we actually take a second to try some other simple inputs, you might notice something interesting. We can actually make a fairly comprehensive base case by noticing that if either one of these dimensions is going to be 1, we have only one unique path. This can be written quite concisely as the following base case. Often with base cases, you want to find a way to be as comprehensive as possible. Don't be afraid to adapt though, it's completely normal to come back later and modify the base case. Let's now take a look at a decent sample size of examples to get a feel for the problem. When coming up with examples for recursive problems, it makes sense to do them in a sweeping manner, where a lot of the examples are really close to each other. Remember, our ultimate goal is to find a way to solve any specific case using simpler versions of that case, so it makes sense to have examples that are close to each other. Alright, so now that we have a sizable set of examples, take a look at these and see if you notice any interesting relationships between cases. I know that's a lot to look at, so as a hint, let's narrow down our focus to just these 3 examples. Do you notice anything? How about now? There's actually a really nice one-to-one correspondence between each path in the 2x3 and 3x2 cases to each path in the 3x3 case. For each path in the 2x3 case, we can take that path and go 1 unit down to create a path in the 3x3 case. And for each path in the 3x2 case, we can move 1 unit right to create a path in the 3x3 case. So, at least in this example, we can confidently say that the number of paths in the 3x3 example is the sum of the number of paths in the 2x3 example and the number of paths in the 3x2 example. But is that just a coincidence? Let's see if we can test this pattern by working backwards. Let's try to find the paths in the 3x4 case by analyzing a similar set of easier examples. Following the earlier pattern, let's see if the number of paths in the 3x4 case is really the sum of the paths in the 3x3 case and 2x4 case. We'll take each path in the 3x3 case and move one to the right to make a corresponding path for the 3x4 case. And then we'll take each path in the 2x4 case and go one step down to make a path in the 3x4 case. And it turns out that the set of paths that are created from this construction end up being all the unique paths to a 3x4 grid. Take a second to verify this for yourself if you're skeptical. So let's now generalize this pattern. We can find the total number of unique paths in an n by m grid by first finding all the unique paths from the n by m minus 1 grid. Each of these paths correspond to a path in the n by m grid, since all we do is we move 1 unit to the right to create an associated path. And the remaining paths can be found by finding all the unique paths in an n minus 1 by m grid, where we now take each path, add 1 unit down, and get the corresponding path in the n by m case. Once we found this general relationship, the hard part is now over. The last thing we do is take this general pattern, bring it together with the base case, and now write code. The corresponding code for such a seemingly overwhelming problem ends up being remarkably simple and elegant, and you'll see this a lot in recursive problems. Speaking of hard problems, let's take a look at a really challenging problem. Here's the problem. Write a function that counts the number of ways you can partition n objects using parts up to m. As we've done so far, let's take a look at some examples to get a sense of what this problem is even asking. For n equals 6 and m equals 4, here's how the partitions work out. We end up with a total of 9 unique partitions. Let's take a look at one more example to make sure we really understand what's going on. Here's what the partitions look like for inputs n equals 5 and m equals 5. Here we have 7 unique partitions, and make sure you take a second to really understand why these are the only valid partitions. Alright, so this problem definitely feels a little intimidating since it's not really obvious how we would even go about starting to solve it. But this is where we're going to have to fall back on our 5 steps. Let's start with step 1. The first thought for what the simplest possible input should be is when n is equal to 0 and m is equal to 0. But what does this mean? What it's asking is how many ways can you partition 0 objects using parts up to 0. This may be a little bit mind-blowing, but there's actually only one partition, and that partition is to include no parts. And in fact, trying inputs n equals 0 with m equals 1 and then n equals 0 with m equals 2 is really no different. This allows you to make another fairly comprehensive base case where the number of partitions is 1 if n is equal to 0. But there's some other simple cases that we should also check out. If n is equal to 1 and m is equal to 0 in these inputs, interesting relationship, we indeed find that more formally, they all happen, and we end up with the same m to each of these parts of our recursive relation. For such a tricky problem, our final solution has to play and work through recursive problem to really be problems of various difficulties. Of how you might have to modify some of your base cases after finding a general recursive pattern. The cool thing about recursion is that for such a tricky problem, our final solution actually ends up being only 6 lines. Lines of code. So, to recap what we did in this video, we went over 5 key steps to solve any recursive problem, and then went about applying these steps to 3 problems of various difficulties. You learned the importance of starting simple and asking yourself what the simplest possible case is. You found it helpful to work through some examples to get a sense for what the recursive problem was asking. You also went about relating hard examples to easy examples to find a generalizable recursive pattern. And then with this pattern in hand, you went about writing the code. As with anything you learned, you're going to have to spend some time to really contemplate and work through recursive problems to really begin to master solving them. This video is all about giving you a mental framework to do that, and I hope it was helpful in that sense. Thanks for watching, and as always, I'd appreciate it if you liked the video if you enjoyed it. If you want to see more content like this, be sure to hit the subscribe button, and if you want to more directly support this channel, be sure to check out the Patreon page, linked in the description below. See you in the next video.
We have an f and it has an argument x. If we, at any point in the function, call the function again, that is a recursive function. So a function that executes itself is a recursive function. So in most cases, you're going to see something like this. You're going to see an x minus 1 in the recursive call of a recursive function. And the reason people do this is because usually you want to change what arguments are passed to a recursive function every time. There are cases where you don't want to change the arguments being passed, but that's pretty rare. So let's actually take a look at how a recursive function flows. So I set up this little animation how this recursive function runs, and I'm going to step through it to really show you what it's doing. So at a very fundamental level, a recursive function like this is going to call itself over and over and over and over again infinitely. And let me show you how this runs. So imagine you have an f, and this f is is taking a 2. So in place of x, we have a 2. And then it calls recursively the f again with 2 minus 1. And when we do that, we get an f with a 1 being passed to it. And then that f is going to recursively be called with a 1 minus 1. So it's going to be a 0. So then we have this function 1 with a 0. And again, it's going to recursively call that 0 with a minus 1. So it's going to be -1. Then a -2, then a -3, and a -4. And this is going to just continue infinitely with no end. This is why we need something called a base case when we run our recursive functions. A base case is simply a way of telling the function, if you ever get to this part of the code, stop recursing and return some result. So here is my example of base case. In this function, a base case is if x is equal to 0, return 0. So we're telling our function, instead of returning the f is not equal to 0. So now we have our f being called with a 1, and again, our x is not equal to 0, so we are going to recursively call our f again. Then our f is equal to 0, so because it's equal to 0, we are going to return 0. This is the base case. This is telling our recursive function to stop recursing. And because of that, it's going to return 0. When it returns 0, it's going to return the value to our function. So it's going to evaluate to 0. Then it's going to return the value to our function again. It's going to value to 0. And the result of this execution is just 0. Here's another example that is kind of more useful. So we have a function f, and this f is taking an x. And if x is equal to 0, it's going to return 1. If it's not equal to 0, it's going to return 1 plus f. So let's see how this runs. We have our f, and we're going to call it with a 2. So if 2 is equal to 0, return 1. That's not the case, so we are going to return 1 plus f. So we have to recursively call our f, and when we do that, we are going to call f with a 1. When we call it with a 1, we are basically doing this whole process again. And finally, we get to our base case. So our base case is if x is equal to 0, then return 1. And because f is being called with 0, we have to stop recursing. We have to return that 1. So that's our base case.
Actually, this is actually a really interesting problem, now that I think about it. Because what is actually asking you to do is to find the boundaries between things. Trying to think on my mind how to solve it, but it's really hard, actually. I think I'm gonna try to solve this, because I do think it's interesting. And the issue is I wanna get the stuff. I might look at the solution, and then because I'm thinking about something different, I might look at the solution just to see the depth first search part, because I don't want to spend time thinking about that, about how to traverse the graph. I'm more interested in what's the logic to get the islands, to get the boundaries. Because what I'm thinking about it is, if you have a fractal pattern inside of a graph, like I was saying before, let's say you have the Mandelbrot set inside of the Cartesian coordinates, then the whole point of the Mandelbrot is the boundary. The Mandelbrot set itself is the boundary of the recursive function, if I remember correctly. So the difference between, so what you're doing is actually, if you find the boundary in wrong resolution of a graph, you actually don't have the full boundary, and the difference is just the size of the graph. So as the size of the graph increases, the configuration of zeros and ones changes, and it gives you a higher resolution of the geometrical structure. So there is a direct correlation between the size of the graph and the geometrical structure that you're analyzing, I think. And by size, I don't mean only bigger, but smaller as well, is the resolution, right, that matters. Which is very interesting to think about. Because you can think about of anything as being a graph or of Cartesian coordinates. And then the functions are the connection between the points. So the function itself is a pattern inside of a graph.
And when we return that, we are returning 1. When we return 1 to our calling function, it's going to evaluate to 1.
Yeah, you can think about a function as being an island of zeros and ones with lower resolution in this case. But as you approach the resolution to infinity, you get the function, I think. Very interesting.
It's going to return a 1 plus 1. So we get 2. Then it's going to return that to our function again. So it's going to be a 1 plus 2. So it's going to give us a 3. So the result of this recursive function is a 3. And let's do one more, but this one's going to be a little more complicated. So in this one, we have a function which is going to call our recursive function plus another recursive function. So if x is less than 1, we're going to return 1. If not, we are going to return f plus f. So let's actually see how this evaluates. So we have our function, and we're going to call it with a 2. And when we call it, we are going to check, okay, if 2 is less than 1, return 1. That's not the case. So we're going to call our f, which is going to call 2 minus 1. And when we do that, we are going to get f with a 1. Then we're going to recursively call it again. So we're going to call it with a 0. And because we are calling with a 0, we are going to return 1 because we hit our base case. Then we're going to return that to our function, which is going to give us a 1 here. Then we're going to execute the other side, and this side is also going to return 1. So the result of that side is going to be a 2. So then we have a 2 plus, then we have to execute the other side of the recursive function. So when we do that, we are going to do the same thing that we did on the one side. So again, we are getting a f1, then a f0, then we are getting a 1, then we are returning that, then we're getting a f0 again, then we're returning that 2, so we get 2, and then we return 2, and we get 4. So that's basically how recursive functions run. It's really useful to visualize recursive functions because when you really see how they run, it really shows you exactly what they're doing, instead of just looking at the code and saying, oh, I have no idea what it's doing, because the syntax isn't really that optimized for recursive function understanding.
In this video, we are going to see about recursion in detail. Let's take a classic example Fibonacci for recursion analysis. Each number in the Fibonacci series is the sum of two preceding numbers. If we add 1 and 1, we will get 2. If we add 1 and 2, we will get 3. If we add 2 and 3, we will get 5. And so on. Let's see the pseudocode for Fibonacci series for better understanding. This is the base condition. When n value comes into the function 1 or 2, then fib function will return 1. This is the recursion call. Recursion means, a function will be called by itself. Here fib function is called by itself. When the base condition fails, recursion call will be happen. This is stack. Stack will track all the function calls. Let's see them elaborately. Our program will start from main function. Main function calls the fib function with n value 5 and main function will be pushed into the stack. Fib function with n value 5 will be called itself with n value 4 and 3. So fib of 5 will be pushed into the stack. Fib function with value 4 will call itself with value 3 and 2. So fib of 3 and fib of 4 will be pushed into the stack. Fib function with value 3 will call itself with values fib of 2 and fib of 1. So fib of 2 will push into the stack and fib of 3 also pushed into the stack. Now fib of 2 will be called itself and fib of 1 will be pushed into the stack. As per our base condition, fib of 2 will return 1. Then, fib of 1 is popped out from the stack and call the function with n value 1. As per our base condition, fib of 1 will return 1. After that, fib of 3 will be popped out from the stack and returns 2 to the previous call. Now fib of 2 will be popped out from the stack and call the function with n value 2. As per our base condition, if n value is 2, then fib function will return 1. Now fib of 4 is popped out from the stack and return 3 to the previous call. Now fib of 3 will be called itself with the values of 2 and 1. As per our base condition, fib of 2 will return 1 and fib of 1 will return 1. Now fib of 3 will be popped out and return 2 to the previous call. Now fib of 5 will be popped out and return 5 to the previous call. Now main function will receive value 5 and prints it.
Implement memoization. So definitely like and subscribe if you are new here, and check out my Patreon if you want to support me further, and let's get into the video. Okay, so let's go over an example. Let's say we were given the following matrix. We need to find the longest increasing path. So in this matrix, it could either be 3, 4, 5, 6, or it could be 2, 4, 5, 6. Both of those paths have a length of 4, so we return 4 from our function. So like I mentioned, we're going to solve this using DFS and memoization. The memoization piece is very, very critical for this problem, because if we didn't do memoization here, then it would just be the brute force approach. But with memoization, we automatically get the optimal approach. So this will make more sense as we go through an example. So the first thing we're going to do is we're going to have a variable called longest path, and this will just be a simple integer value that we initialize to 0 that keeps track of, you guessed it, the longest path as we are iterating through this matrix. So we're going to loop over each position in the matrix and compute the longest path at each step. In each direction that we check, a recursive call is going to be made determining the longest path in that direction. So to start things off, we have our I pointer. We're going to start it at position 0, 0, so it's looking at the number 3. So we are going to continuously check all of our neighbors from every single position in this matrix to see if they're greater than our current position. So starting at 0, 0, if we look to the left of us, that's out of bounds. So this specific recursive call will just return 0. There's no path in the left direction. Likewise, we're going to look up. That is also out of bounds, so we return 0 from the up direction. If we look down, that has a number 3. Well, 3 is equal to 3, and we're looking for a path that is strictly greater. So we're just going to ignore this down direction as well, so we're going to return 0. And then finally, if we look to the right of position 0, 0, we see that we have a 4. And 4 is greater than 3. That is strictly greater. So that means we are going to do another recursive call at position 0, 1 now. So far, all of our directions except the right direction has returned 0 from its own recursive call. So now we're at position 0, 1. If we look to the left of us, 3 is less than 4, so we return 0. If we look above us, that's out of bounds, we return 0. If we look down, 2 is less than 4. Once again, we're going to return 0. And then finally, if we look to the right, 5 is greater than 4, so that means we're going to make another recursive call to position 0, 2. So what we're doing right now is the actual DFS portion. The memoization comes in a little bit. So at position 0, 2, our left, up, and right directions, we are going to return 0 because each of those directions either are out of bounds or the numbers are less than what our current number is at. However, if we look down at this position, 6 is greater than 5, and that means we're going to make another recursive call to position 1, 2. The directions up and left are less than our current position, so we're going to return 0, and then our right and down directions are out of bounds, so we're also going to return 0 from those directions. And so here is the interesting part of this recursive algorithm. At position 1, 2, we have completely exhausted looking in all of the directions. So now what we're going to do is get the maximum in all directions. So we get the max from the left, up, right, and down, and that would just be 0. And then with this maximum that we've computed, we're going to plus another number 1 to it. The reason why we add 1 is because our current position alone is a path of size 1. Right now, 6 by itself is its own strictly increasing path. The reason why we have to compute the maximum in all directions is because, once again, we're trying to find the longest path. We don't want to get the minimum, we want the very maximum that we can find. And now on to the memoization portion. Memoization means to cache previous recursive calls that we have already made. Doing this will save many steps in a recursive algorithm. So what we're going to do is initialize a 2D matrix that has the same number of rows and columns as our input matrix. Right now, all of the positions in this matrix are just initialized to 0. But now what we're going to do is update our current position in our cache to just be 1, the value that we just computed. So right now we're looking at position 1, 2. So at position 1, 2 in our cache matrix, we're going to put that value that we computed. So that way, if we ever end up at position 1, 2 again, we can just return the cached value. And so now we're going to go back down the call stack that we made. So from position 1, 2, we are going to return the value 1. So at position 0, 2 now, our down direction is taking that value of 1. So then we're going to do the same thing. We're going to get the maximum in all the directions from position 0, 2, which would just be 1. And then we plus another 1 to account for the current position for a total of 2. And then just like before, we're going to update our cache again. Our current position is 0, 2. So then we're going to put 2 in our cache. And then from position 0, 2, we're going to return 2 back to position 0, 1. Position 0, 1's right direction has a value of 2. We get the max in all of the directions, which is 2, plus another 1 for the current position for a total of 3. Once again, we update our current position in the cache, which would be a total of 3. Finally, from position 0, 0, our right direction is returning 3. So we get the maximum in all of the directions, which would be 3, plus another 1. We update our current position in the cache. 3 plus 1 is 4. So now, as you can see, we've exhausted all of our recursive calls starting at position 0, 0. So we're going to update our longest path variable that we initialized in the beginning to be 4. Now that we've done that, we're just going to continue iterating through our matrix, and we're going to perform a value of 1. So we've over our matrix, our longest, this one. All right, so let's jump to this path. So we'll say M. So it's the same size as our input matrix. And now what we want to do is start iterating over all of the elements in our matrix. So now that we have these nested for loops, this is where the DFS is going to come into play. We need to write a recursive algorithm that is called on every iteration of each loop. So let's come in here, we'll say int, and we're going to compute the longest path. Let's just assume that we have this function right now. So we'll say int longest, and we can call it longest increasing path. And we're going to pass in a couple things to this recursive function. Well, obviously, we're going to need our matrix. We're also going to need our cache that we initialized above. We're also going to need the rows, columns, rows, columns, and then our current position. So we'll say n, m, and then our current position will be I and j. So assuming that we have this recursive algorithm written, we just need to compute our maximum. So we'll say longest path equals math.max between longest path and longest. And then when we come out of this for loop, we just return the longest path. So now all we need to do is implement this longest increasing path recursive DFS function. Okay, so I've written out the method signature. The first thing we want to do is check if we've already been at this position before. And we can do that by seeing if our current cache position is 0 or not. So what we can do is we're going to say if cache at position I, j, if it's greater than 0, that means we have computed this position already. And we can just return cache at I, j. So this part is exactly the memoization piece that we discussed. If we make it outside of this if statement, we have not been at this position before. And this is where we're going to check all of our neighbors, so the up, right, down, and left positions. So the first thing we can do, let's initialize a variable. We can say max. And another thing, since we need to check all directions, we can initialize up here a bound direction. Bounds, and if it's strict at ij equals z, I get a time limit I have to initialize.
Hey guys, welcome back to another episode of Coffee and Algorithms. Today we're checking out a question called max area of islands, something like that. It's a 2D matrix question involving breadth first search or depth first search, whichever you prefer. If you're struggling with any of those concepts, I recommend this videos. We'll break it down and make it super simple. Again, today I'm back with Paul, my good friend who is a local expert in algorithms and data structures. You can find links to the channel below. Right, enough of me talking. Let's get to the video. Alright, so if we consider this 2D matrix here, we can see that we have ones and zeros only. Now, for this example, the ones can represent land, and the 0 can represent water. And so, if we define
it's the question that I'm trying to solve.
Ones, such that the ones are surrounded by water, and then in this example, we'll consider outside of the matrix to be water as well. So I want you to write a function that, given this 2D matrix, you tell me the size of the largest island in the matrix.
Okay, so from what I understand, the island can be connected 4 ways, right?
It's slightly different.
Right here.
Yeah, that's right.
So that's one. So I'm guessing like something like this, where it's connected diagonally, would not count as an island.
Yeah, you can't have diagonal touching land.
We have 2 separate islands.
Yeah.
So in our function, we'll be given a 2D list, right? And would the numbers be integers, or would they come as strings, or
integers?
Integers, right? Okay. So I think for this problem, particularly when doing graphs, we can use something like breadth first search or depth first search, graph traversal algorithms to traverse the graph. So I think we can use something like depth first search, and we can start at the top left element, and we'll use depth first search to count the number of ones we have for a given island.
Okay.
And we'll do that for every single island, so we'll traverse the whole matrix, and basically, if we have one, if we find one, then we can use depth first search to work out the area of that given island. And then maybe we could sync the island as well, so that doesn't intervene.
What do you mean by sync the island?
So basically turn the ones into zeros.
Okay, so to sort of show that you've traversed it, so you've seen that already?
Yeah, so it would improve the computational complexity of the algorithm, make it more efficient.
Could you sort of show me an example of how depth first search might work on this?
Yes, so depth first search is an algorithm where you basically explore down as far as possible down one path before backtracking. So if we start at top left corner, we would, for example, go down and keep going down until we reach a 0, and then we'll have to go back up and explore on the right, and then go back up as well, and explore on the right from here. So it's quite a good algorithm for for traversing graphs.
Okay, and how would breadth first search look different?
So breadth first search really works by exploring all the neighbor elements, all the neighbor nodes before moving down deeper, essentially.
Okay.
So if we start from our first element here. Of grid I. So length of the current row. Yep. And yeah, we'll get the current area count by calling our help function, and we'll pass in the grid and the current I and j.
Okay. And that's not the implementation I'm looking for. I'm looking for one that traverses the graph without doing a nested for loop. Just doing the depth first search. But maybe I'm messing it up or mixing it up the problems that I saw before. I'm confusing one problem that I saw before with this one. So it might not be possible to traverse, but I think it should be. I don't see any reason why it wouldn't be. What I want is to find the if conditions on a recursive function that allow you to go over all the nodes in the matrix. Is it even possible to do that, actually, now that I think about it? Because it's one thing to generate the fractal, but it's another thing if you have the matrix with the fractal, how can you create an algorithm to get that? I guess you can just look for the points in the graph. You can look at the data. Yeah, but then it becomes a question of overfitting and underfitting in machine learning, I think. Is it trying to find a fractal in data. And this one looks interesting.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
The library will be closing in 15 minutes at 2 o'clock. At this time, please begin to exit the building. Thank you.
All right, so today we have a fundamental graph question. We don't see a graph here, but the thing is, whenever we have something with nodes, with relationships, with connections, we can represent those connections and relationships with a graph. And when we have a maze like this, we can represent each of these cells as a node and each of the adjacent relationships as an edge. Whenever we can represent a node and an edge, we are able to create a graph structure to make a representation of this. That is what this is. This is a maze, and our interviewer says, write me an algorithm to search this maze. So if you're in an interview, you're not going to have to do any difficult algorithms like A star or something that's very efficient that works off of heuristics. What you're going to have to do is, you're going to have to work on your fundamentals. So we know our fundamental graph searching algorithms are going to be breadth first search and depth first search. We're going to start, we're going to end, and we're told to find a path. We're not told to find the shortest path, we're just told to find a path. Find me a path in this maze. So how will we do this? Now, if I use breadth first search, I'm always going to get the shortest path from start to end. Why is that? Well, breadth first search does. Breadth first search starts, it's going to go outwards breadth. It's going to go like this, and then like that, and then like that. It's going to go layer by layer, going outwards from the start. So the thing is, when we hit this end, we're going to have gone out layer by layer. And when we hit that end, that means we're going to be in the layer that the end falls in. So the thing is, it's going to be the shortest path because of the nature of how we searched. If we use depth first search, as we're going to see, it's going to take us all the way in here. It's going to take us all the way in here. It's going to take us all the way there to the end. It might not give us the shortest path, but it's going to give us a path. And that's what depth first search will do for us. I already have a video on depth first and breadth first graph search. If you want to check that out, check that out. But what we're going to do is we're going to do depth first search because it's fairly easy to implement. And remember, the code is in the description. The code is in the description for this. So if you want to see how the solution pans out, how the recursion pans out, out, you're free to go check that out. I think it's a great resource. So search this maze. So when we're doing a search, or whether it's breadth first or depth first, we need to understand our fundamental choice. Our fundamental choice at each of these cells. What can we do at each of these cells? Each of these cells represents a choice. So when I'm at any of these cells, my fundamental choice is going to be go up, go right, go down, or go to the left. When can I not do these? I cannot do it if it's a black cell. A black cell is a wall. I cannot do it if I'm looking down and I'm at an empty, I'm in a cell out of the maze. I can't do that. So what I need to do is first understand my fundamental operations, and second, validate whether I can actually perform them. If I'm sitting at this cell, I can go up, I cannot go right. I can go down, but I can't go backwards. Why can't I go backwards? Well, we're going to be starting here at the start, and we can't traverse backwards in our path. So every time we initiate a search from a node, we're going to mark that node as search. We're going to mark that node as untraversable because we're performing a search off of it. We can't go backwards in our path. We're going to have an infinite recursion. We're never going to find a path, and everything's going to be messed up. So what we're going to do is we're going to kick off our search. We're going to start right here. We're going to mark the cell as traverse, and then what we're going to do is say, can I go up? Can I go right? Can I go down? Can I go left? All right, we marked it as traverse. This blue marker is going to put a little dot on the search we're going into deep. So can I go up? No, I cannot. Can I go to the right? Yes, I can. Let me go to the right. That blue dot is telling me that I'm going depth first. I'm going deep into a search into here. And if this doesn't work out, I'm going to come right back here. And then I'm going to look down. And then I'm going to look left. It turns out we can't go down or left. But if this fails, if this depth first search, depth first fails, we come back here and then we try down and then we try left. But right now we're going depth first into right. So what we're going to do is we're going to go to this right guy. And now we're going to mark this reverse. And now what do we do? What is our choice at every node? We go up, right, down, left. Can I go upwards? Of course I can. We have a white cell. That's clear. We're not in a wall. We're not going out of bounds. So what I do is I go depth first and I put a dot. Okay. And now you see we're going depth first on here. We're going depth first upwards. So all along this thing, we're going to keep these in a path. We're going to keep it in an array list symbol. Nothing complicated. We're going to keep this in an array list. Keep this in an array list. If it doesn't work out, we'll just pop the item off and then we're not going to have to worry about it being in a path because it didn't work out. So now we're up here. Can I go upwards? Yes, I can. But I don't even notice. Do you see the problem we're going to run into? This is going straight to a dead end. Well, we'll see how we handle that. But the thing is, this is why this is kind of naive. This is why these raw algorithms like depth first search without heuristics to sharpen them are naive because we'll go deep. We'll go depth. We'll go deep into this path. And we won't even know this is over here. That's over there. Well, why are we doing this? But that's just the nature of the search. So that's what I want you to notice in this. So now we need to mark this as traverse. Can we go up? Yes, we can. So now we're at this cell. So now I mark this cell traverse. Can I go up? No, I cannot. That's a wall. Can I go right? No, I cannot. That's a wall. Can I go down? I can't. Can I go back? This cell left didn't work out. But what you notice is this up. No, I can't. Can I go back? We go to this guy. Down did not work out. So now he's going to return to his caller. But it returns to his caller saying, I have a path to the end. Our base case, if I am the end, then I have a path to the end. And we are going to have the path from start to end. This is how depth first search works. I hope this was a clear cardinality. So the time complexity is we're going to be traversing the node.
Where's the code? Ah.
Okay, now clustering for graphs. So this is a topic. This is one of the important things you can try to do with a graph. So you have a large graph.
You're just gonna search for the solution, or whatever. And this is C++. This was the thing that I wasn't sure about. But I guess I was in the right track. But then I also couldn't think about how to create something that checks to see if it is an island or not. So it just returns if it is a 1. And then it goes in all directions. But I guess you have to loop on... I was trying to avoid doing this, but I guess you have to. I thought that it would be possible to just do these things here, and then you wouldn't have to do this. But I don't understand how this works. It doesn't make a lot of sense to me. Because it's counting every time that is that there is a 1 here. So I don't see how it works. Oh, it starts the search every time there is a 1, but then it adds to the count. And then, yeah, so every time it hits a 1, it adds to the count and starts calling recursively to find all the cells from that position. I don't get it though. Nice, same thing from the other guy. I'm gonna search for the solution to see, because there's probably a neat code video about it. Probably gonna be easier to understand.
Hello guys, welcome back to TechDose, and in this video we will see the number of islands problem, which is from lead code day 17 of the 30 days coding challenge. So let us look at the problem statement. The problem here says that given a 2D grid map of ones and zeros, where 1 denotes land and zeros denote water, count the number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. You may assume all 4 edges of the grid are all surrounded by water. So let us now look at some examples in order to get a better understanding. Let us see the first example. In this example, you can see that all the ones are connected. So we can say that there is only one island. So this is a single piece of land, and therefore we have only one island. And how is the connection defined? A connection is defined only in 4 directions. That is, a piece of land will be connected to other land only if it is adjacent and it is present in either vertical or in horizontal direction. Like the point I mentioned, connection between piece of land is only in vertical and horizontal directions and not in diagonal. So this is a single piece of land. In the second example, you can see that these 2 pieces of lands are connected, so this forms a single island. This piece of land is alone, so this is a second piece of land, and this piece of land is also alone, this is a third piece of land. Therefore, the total number of islands is 3. Even though they are diagonally connected, we do not include these diagonal connections. We only care about vertical and horizontal connections, so they are not connected here. So I hope you understood the problem statement. Now, what solution intuitively comes to your mind? A very intuitive method is by using DFS, that is depth first search, or you can also use breadth first search for this problem. So let us see how to apply DFS or BFS for this problem. Now, I have taken a different example, a larger matrix, and in this problem, our goal is to mark an island in just one DFS call. So if we make a DFS call, then we will cover that entire island and mark it as visited. So if you are at a cell x, y, then we can traverse in either top down or left right directions. So if our current coordinate is x, y, then we will have to search in all the 4 directions, and so the coordinates passed will be like, if you are calling to the top cell, then it will be x minus 1, y. This is the adjacent top cell, and similarly you can call in all the 4 directions. So these all coordinates are extremely easy to understand, I think. So let us just process this example and find out how many islands are there using our algorithm of DFS. So I will start from the 0th column and 0th row, that is from 0, 0. So I will use standard 2 loops, and then I will iterate for each and every cell. Now as soon as I see a 1, this indicates that this will form an island. So as soon as I see a 1, I will have to mark the entire island. So what I will do is I will just visit this cell and then mark all the adjacent cells as well, which are present in the same island. So for keeping track of the answer, we will take the number of islands variable and we will mark it as 0 initially. Initially we will assume that we don't have any island. As soon as we see a 1, I will just increment the number of islands by 1, and then I will mark the entire island. So how it is done? From this current piece, I will just convert it to 2. Now here 0 indicates water, 1 indicates land, and 2 will indicate that the land is visited. So this will be a visited land. Why I have taken 2? You can take any other number, but it should not be 1, because we are considering that 1 is not visited. You can even mark it as 0. It won't matter. So I have taken here 2 just to make it look separate from this water. So I'll mark it as 2. Now I will make call in all the 4 directions. That is in top, left, right, and down. So I have already handled the boundary cases of this out of bound cases. So this we won't process. It will just return, and we will move on to the next cell, which is 1. So from this we will move right. This is also 1. We will mark it as 2. Now from this cell as well, we will make 4 different calls. So these will be the calls, and this top and left calls will not be processed because top is out of bounds, and on the left hand side you find a number 2. This means that this has already been visited. So you will just return from there. On the right hand side you have 0. So this will also not be processed. It will just be returned. And on the down you have 1. So this will be made as 2. And then again you will make 4 different calls: top, right,
Oh,
down,
I
left.
understand now, I think. So when you return zone the depth first search, it just keeps searching, and it gets pretty much all the ones that are connected with the other one. I get it now. Then once it does that, it counts, increases the count, and goes back to. Yeah, but how doesn't it count more than one if? Oh, because you already visited. So you're changing the value of the ones as you visit them. So in the outside, on the nested for loop outside, you're not gonna visit them again. That's what's happening. But inside of here, they're not changing the value. I guess they are. In the previous one, I think they were making equal to a hashtag. Yeah, makes it equal to true. It still seems inefficient to me. It feels like there must be a better way to do this, but maybe there isn't, because there's no solution that is better from the ones presented here. Because I thought the whole point of doing the depth first search was to avoid doing the nested for loop, but I guess you can't avoid it. So you're doing multiple different for loops, I guess. The nested one should search for all the elements, and then for each element you're doing an entire search again. But you're only searching for until you get all the elements, I guess. So yeah, and then in the outer for loop, nested for loop, you're not gonna go through each element, because as you're gonna change the elements inside of the depth first search function.
So all these calls will be made. The top one is already visited, so you will just return from there. Right side is 0, so this will also be returned. Down is also 0, it will also be returned. On the left hand side you have 1, so you will mark it as 2. And then you will again make calls in all the 4 directions. Now left is out of bounds, down is 0, right hand side is already visited, and top is already visited. So all these 4 calls will get returned, and similarly we will return back to this first cell. Now this first cell has been processed. So we had seen our 1 initially at 0, 0. So our ith loop and jth loop values are just 0, 0, and this value was 1, so we had increased this number of islands to 1. And we have marked this entire island. So after marking, this bunch will look like 2, 2, 2, 2. And the adjacent cells are 0, 0, 1, 0, 0. Okay. And there are many other cells as well. So these are all marked. Now we have processed this first cell. Now we will move on to the next cell. This is 2. Now this is not 1. So we will not do anything. We will not process it since this is already visited. We move to the next cell, which is 0. So
maybe the alarm went off and then just kept going. I think I'm gonna watch this video and then I'm gonna eat something while I watch this video. I think what I'm gonna do is try to explore this. It seems more interesting to me than trying to solve lead code problems. And I think I'm gonna learn more if I do something that I'm interested on.
Here it is at 0, 2. This is 0, so we won't process it. So all the zeros will be skipped. After this, we will come to row number 1. So in this row number 1 and column number 0, we have value 2. This means this is a piece of land, but we have already visited, so we won't process it. So we move to the next island. This is 2 as well, so this has already been visited. This island is already marked, so we will move to next point 0. So this is a 0. Zeros are not processed since they are water bodies, so they all will be skipped. These zeros will be skipped. Now we are in row number 2, column number 2. So this is the one. Since this is 1, this indicates that the island it belongs to has not yet been visited. So we will just increase the count of number of islands because this is a new island which we found, and then we will mark it as 2, saying that this cell is visited. Now we will mark the entire island. So we don't know what is the size of this island. So we will make calls in all the 4 directions, top, down, and left, right. So the top is 0, right, left, down, all are zeros. So all will get returned, and no cells will be processed further. So now we have processed this cell. This is now 2. We move on to the next cell. This is 0. We will not process it since they are water bodies. After that, we will encounter this one. Now since we have encountered one, this indicates that we have found a new island, because in every DFS call we are making sure that all the piece of lands are marked which are present in an island. And since we are finding a new one, this indicates that this is a new island. So we will increase the number of islands. It will now become 3, and we will mark the entire island. Now we don't know the size of it, so we will make call in all the 4 directions. So top is 0, left is 0, and down is out of bounds. So these all will return. And after that, we go to right. So this right value is also 1, so this will be processed. We will make calls in all the 4 directions, and before making the call, we will just mark it as 2. So this top is 0, right and down are out of bounds, and left is already visited. This will be 2 actually. So all of them are already processed or out of bounds, so they will be returned. Now we have visited all the cells, and whatever the number of islands count is there, these are the total number of islands which are present in our grid. So I hope you understood this simple DFS approach. What is the time complexity of this approach? The time complexity is order of n only, because in the worst case we are traversing a single given cell 2 times, and the space complexity in this case you can say that it is O1, considering that the recursive calls will not take any extra space. But then you already know that in recursive calls we require stack memory. So if stack memory is sufficient and if it is possible to neglect it, then space complexity will be O1. But in this case, what will be the memory used? The memory used will be order of number of recursive calls, and the number of recursive calls in the worst case will be equal to m into n if our matrix size is m by n. Because in the worst case, each and every cell will be having value 1, and so you will make recursive calls like a snake. It will just be like a snake. You will just go in depth. So the depth of this recursive call can go to maximum m by n, and so m by n is given, and that will be multiplied by the memory which you are using for each recursive call. So memory for each call. Now for each recursive call, we might pass an array or we might pass some variables, so that will get added actually m by n times, or you can say that it will be multiplied m by n times. So let us now look at the simple DFS code which I have written. You can see that we are given the grid, and from this grid I found the number of rows. If the rows are 0, this indicates that this grid is empty, and so no islands can be found, and therefore I will return the 0. Otherwise, if the rows are not empty, then I will find the number of columns, and this will give m by n, which is the matrix size. After that, I will initialize the number of islands as 0, and then I will iterate for each and every cell in the matrix. When we find that the current cell is equal to 1, that is, this is a piece of land which is not being visited, this indicates that we have found a new island, because we are solving this question considering that when we visit a piece of land which is not visited, then we are marking that entire island as visited using this DFS call. So since we are seeing this one, this indicates that we have found a new island, since we had already marked all the piece of lands of the islands which we had visited. So what I will do is I will first mark the current island, and after marking the current island, I will increase the number of islands, and finally after processing all the cells, I will just return the number of islands. Now let us see this recursive call which is mark current island. So this is the recursive call. This is very simple actually. Here this matrix is taking the grid which was passed to us, this one. Now this x comma y is our current coordinate of the cell, and this r comma c is denoting m by n, which is the size of our grid. Now first 4 conditions of this statement is taking care of the boundary case, and the last one is just seeing whether this is a piece of land which is not visited. If this is not a piece of land which is not visited, or if it is a piece of water body, then we will just return from here. Otherwise, if it is a new piece of land, then we will mark it as visited. So we have already assumed that 2 means that it is visited. After marking it visited, I will make a recursive call to down, right, top, left, that is in vertical and in horizontal direction. The only parameter which needs to be changed is this x and this y, because if you go down from x comma y, then obviously your coordinate will change to x plus 1 comma y, and similarly for all the 4 directions. So you need to change the current location of your cell which you will be processing, and rest all will be same. So you can either use a for loop, but then I have not used for loop, I just wrote 4 lines. Now this question can also be solved by using disjoint sets, but then I have never explained you this approach, therefore I went with the easy approach. If you have any other approach or any other solution in different languages, then you can just provide below in the comment section so that everyone can benefit from it. As usual, the code link will be present below. If you have any type of doubt, then feel free to comment below, and I'll try to help you as soon as possible. Like and share our video, subscribe to our channel, and watch more of this programming video. See you on next video. Thank you.
I'll go grab something to eat, and I'm gonna eat watching this video right back.
clusters. Okay. So you get a giant graph, and the job is to make some sense out of it. And one possible step is to be able to subdivide it if, as I see here, there's a cut between two reasonably equal parts of the graph, reasonably same size, and therefore that graph could be studied in two pieces. So the question is, how do you find such a cut by a algorithm? What's an algorithm that would find that cut? So that's the problem. Let's say we're looking for two clusters. We could look for more clusters, but let's say we want to look for two clusters. So what are we trying to do? We're trying to minimize. So this is the problem then. So we look for find positions x and y, let's say, two, which will be the centers, so to speak, of the, and really it's just these points. So the data is the points and the edges, as always, the nodes and the edges. So the problem is to find x and y so that to minimize, so it's a distance of points ai from x, maybe should emphasize we're in high dimensions, plus the distance of other points. So the ai will be these points, these nodes, and the bi will be these nodes, plus the sum of bi minus y squared. And you understand the rule here, that together, the a's union the b's give me all nodes. And I guess to be complete, the a's intersect the b's is empty. Just what you expect. I'm dividing the a's and the b's into two groups, and I'm picking an x and a y sort of at the center of those groups, so that that is a minimum. So I want to minimize. And also, I probably want to impose some condition that the number of a's is reasonably close to the number of b's. In other words, I don't want just that to be the a and all the rest to be the b's. That would be not a satisfactory clustering. I'm looking for clusters that are good-sized clusters. So minimize that. Okay, so there are a lot of different algorithms to do it. Some are more directly attacking this problem. Others use matrices that we associate with the graph. So let me tell you about two or three of those algorithms. And if you've had a course in graph theory, you may already have seen this problem. First question would be, suppose I decide these are the a's and those are the b's, or some other decision. Yeah, probably some other decision. I don't want to solve the problem before I even start. So some a's and some b's. What would be the best choice of the x once you've decided on the a's? And what would be the best choice of the y once you've decided on the b's? So we can answer that question. Just if we knew the two groups, we could see where they should be centered, with the first group centered at x, the second group centered at y, and what does centering mean? So let's just say, so I think what I'm saying here is, let me bring that down a little. So given the a's, this is a1 up to, say, ak, what is the best x? Just to make that part right. And the answer is, do you know geometrically what x should be here? X is the, so if I have a bunch of points and I'm looking for the middle of those points, the point x, a good point x to say, okay, that's the middle, it'll make the sum of the distances, I think, squared. I hope I'm right about that. A minimum. What is x? It is the centroid. Centroid is the word. X is the centroid of the a's. And what is the centroid? Let's see. Oh, maybe I don't know if x and y were a good choice, but let me see what. I guess it's the average a. It's the sum of the a's of these a's. Those are vectors, of course, divided by the number of a's. I think. Actually, I was just quickly reviewing this morning, so I'm not totally on top of this centroid. What I'm going to talk about, the algorithm that I'm going to talk about is k. Well, k-means it's always called, and here it will be k will be 2. I just have 2 partitioning into 2 sets a's and b's, so k is just 2. Okay, what's the algorithm? Well, if I've chosen a partition, the a's and the b's have separated them, then that tells me what the x and the y should be. But now what do I do next? So this is going to be a sort of an alternating partition. Now I take those 2 centroids. So step 1 is, for given a's and b's, find the centroids x and y, and that's elementary. Then the second step is, given the centroids x and y, given those positions, given x and y, they won't be centroids when you see what happens. Given x and y, form the best partition, best clusters. Okay, so step 1, we had a guess at what the best clusters were, and we found their centroids. Now we start with the centroids and we form new clusters again. And if these clusters are the same as the ones we started with, then the algorithm is converged. But probably won't be, these clusters. So you'll have to tell me what I mean by the best clusters. If I've got the 2 points x and y, I want to separate all the points that cluster around x to the ones that cluster around y, and then they're probably different from my original start. So now now I repeat step 1. So, but let's just say, how do I form the best clusters? Well, I take a point and I have to decide, does it go with x, or does it go in the x cluster, or does it go in the cluster around y? So how do I decide that? Just whichever one it's closer to. So each point goes with, each node, I could say each node goes with the closer of x and y. So points that are closer to x, now we're going to put them in the cluster around x. And does that solve the problem? No, because, well, it might, but it might not. We have to come back to step 1. We've now changed the clusters. They'll have different centroids. So we repeat step 1, find the centroids for the 2 new clusters. Then we come to step 2, find the ones that should go with the 2 centroids, and back and forth. I don't know. I don't think there's a nice theory of convergence or rate of convergence, all the questions that this course is always asking. But it's a very popular algorithm, k-means. K would be to have K clusters. Okay. So that's I'm not going to discuss I'd rather discuss some other ways to do this, to solve this problem, but that's one sort of hack that works quite well. Okay, so second approach is what's coming next. Second solution method. And it's called the spectral clustering. That's the name of the method. And before I write down what you do, what does the word spectral mean? You see spectral graph theory, spectral clustering. And in other parts of mathematics, you see that where you see spectral theorem. I gave you the most, and I described it as the most important, perhaps, theorem in linear algebra, at least one of the top three, is, so I'll write it over here because it's not, it doesn't, it's the same word, spectral. Well, let me ask the question again. What's that word spectral about? What does that mean? That means that if I have a matrix and I want to talk about its spectrum, what is the spectrum of the matrix? It is the eigenvalues. So spectral theory, spectral clustering is using the eigenvalues of some matrix. That's what that spectral is telling me. Yeah. So the spectral theorem, of course, is that for a symmetric matrix S, the eigenvalues are real and the eigenvectors are orthogonal. And don't forget what the real full statement is here, because there could be repeated real eigenvalues. And what does the spectral theorem tell me? For symmetric matrices, if lambda equals 5 is repeated 4 times, if it's a 4 times solution of the equation that gives eigenvalues, then what's the conclusion? Then there are 4 independent orthogonal eigenvectors to go with it. We can't say that about matrices, about all matrices, but we can say it about all symmetric matrices. And in fact, those eigenvectors are orthogonal, so we're even saying more. We can find 4 orthogonal.
Eigenvectors and eigenvalues is one of those topics that a lot of students find particularly unintuitive. Questions like, why are we doing this and what does this actually mean, are too often left just floating away in an unanswered sea of computations. And as I put out the videos of the series, a lot of you have commented about looking forward to visualizing this topic in particular. I suspect that the reason for this is not so much that eigenthings are particularly complicated or poorly explained. In fact, it's comparatively straightforward, and I think most books do a fine job explaining it. The issue is that it only really makes sense if you have a solid visual understanding for many of the topics that precede it. Most important here is that you know how to think about matrices as linear transformations, but you also need to be comfortable with things like determinants, linear systems of equations, and change of basis. Confusion about eigenstuffs usually has more to do with a shaky foundation in one of these topics than it does with eigenvectors and eigenvalues themselves. To start, consider some linear transformation in 2 dimensions, like the one shown here. It moves the basis vector I hat to the coordinates 3, 0, and j hat to 1, 2. So it's represented with a matrix whose columns are 3, 0, and 1, 2. Focus in on what it does to one particular vector, and think about the span of that vector, the line passing through its origin and its tip. Most vectors are going to get knocked off their span during the transformation. I mean, it would seem pretty coincidental if the place where the vector landed also happened to be somewhere on that line. But some special vectors do remain on their own span, meaning the effect that the matrix has on such a vector is just to stretch it or squish it, like a scalar. For this specific example, the basis vector I hat is one such special vector. The span of I hat is the x-axis, and from the first column of the matrix, we can see that I hat moves over to 3 times itself, still on that x-axis. What's more, because of the way linear transformations work, any other vector on the x-axis is also just stretched by a factor of 3, and hence remains on its own span. A slightly sneakier vector that remains on its own span during this transformation is -1, 1. It ends up getting stretched by a factor of 2. And again, linearity is going to imply that any other vector on the diagonal line spanned by this guy is just going to get stretched out by a factor of 2. And for this transformation, those are all the vectors with this special property of staying on their span. Those on the x-axis getting stretched out by a factor of 3, and those on this diagonal line getting stretched by a factor of 2. Any other vector is going to get rotated somewhat during the transformation, knocked off the line that it spans. As you might have guessed by now, these special vectors are called the eigenvectors of the transformation, and each eigenvector has associated with it what's called an eigenvalue, which is just the factor by which it's stretched or squished during the transformation. Of course, there's nothing special about stretching versus squishing, or the fact that these eigenvalues happen to be positive. In another example, you could have an eigenvector with eigenvalue -1/2, meaning that the vector gets flipped and squished by a factor of 1/2. But the important part here is that it stays on the line that it spans out without getting rotated off of it. For a glimpse of why this might be a useful thing to think about, consider some 3-dimensional rotation. If you can find an eigenvector for that rotation, a vector that remains on its own span, what you have found is the axis of rotation. And it's much easier to think about a 3D rotation in terms of some axis of rotation and an angle by which it's rotating, rather than thinking about the full 3x3 matrix associated with that transformation. In this case, by the way, the corresponding eigenvalue would have to be 1, since rotations never stretch or squish anything, so the length of the vector would remain the same. This pattern shows up a lot in linear algebra. With any linear transformation described by a matrix, you could understand what it's doing by reading off the columns of this matrix as the landing spots for basis vectors. But often, a better way to get at the heart of what the linear transformation actually does, less dependent on your particular coordinate system, is to find the eigenvectors and eigenvalues. I won't cover the full details on methods for computing eigenvectors and eigenvalues here, but I'll try to give an overview of the computational ideas that are most important for a conceptual understanding. Symbolically, here's what the idea of an eigenvector looks like. A is the matrix representing some transformation, with V as the eigenvector, and lambda is a number, namely the corresponding eigenvalue. What this expression is saying is that the matrix vector product, A times V, gives the same result as just scaling the eigenvector V by some value lambda. So finding the eigenvectors and their eigenvalues of a matrix A comes down to finding the values of V and lambda that make this expression true. It's a little awkward to work with at first because that left-hand side represents matrix vector multiplication, but the right-hand side here is scalar vector multiplication. So let's start by rewriting that right-hand side as some kind of matrix vector multiplication, using a matrix which has the effect of scaling any vector by a factor of lambda. The columns of such a matrix will represent what happens to each basis vector, and each basis vector is simply multiplied by lambda, so this matrix will have the number lambda down the diagonal, with zeros everywhere else. The common way to write this guy is to factor that lambda out, and write it as lambda times I, where I is the identity matrix with 1s down the diagonal. With both sides looking like matrix vector multiplication, we can subtract off that right-hand side and factor out the V.
So what we now have is a new matrix, A minus lambda times the identity, and we're looking for a vector v such that this new matrix times v gives the 0 vector. Now, this will always be true if v itself is the 0 vector, but that's boring. What we want is a non-zero eigenvector. And if you watch chapter 5 and 6, you'll know that the only way it's possible for the product of a matrix with a non-zero vector to become 0 is if the transformation associated with that matrix squishes space into a lower dimension. And that squishification corresponds to a 0 determinant for the matrix. To be concrete, let's say your matrix A has columns 2, 1, and 2, 3, and think about subtracting off a variable amount, lambda, from each diagonal entry. Now imagine tweaking lambda, turning a knob to change its value. As that value of lambda changes, the matrix itself changes, and so the determinant of the matrix changes. The goal here is to find a value of lambda that will make this determinant 0, meaning the tweaked transformation squishes space into a lower dimension. In this case, the sweet spot comes when lambda equals 1. Of course, if you had chosen some other matrix, the eigenvalue might not necessarily be 1, the sweet spot might be hit at some other value of lambda. So this is kind of a lot, but let's unravel what this is saying. When lambda equals 1, the matrix A minus lambda times the identity squishes space onto a line. That means there's a non-zero vector v such that A minus lambda times the identity times v equals the 0 vector. And remember, the reason we care about that is because it means A times v equals lambda times v, which you can read off as saying that the vector v is an eigenvector of A, staying on its own span during the transformation A. In this example, the corresponding eigenvalue is 1, so v would actually just stay fixed in place. Pause and ponder if you need to make sure that that line of reasoning feels good. This is the kind of thing I mentioned in the introduction. If you didn't have a solid grasp of determinants and why they relate to linear systems of equations having non-zero solutions, an expression like this would feel completely out of the blue. To see this in action, let's revisit the example from the start, with a matrix whose columns are 3, 0, and 1, 2. To find if a value lambda is an eigenvalue, subtract it from the diagonals of this matrix and compute the determinant. Doing this, we get a certain quadratic polynomial in lambda, 3 minus lambda times 2 minus lambda. Since lambda can only be an eigenvalue if this determinant happens to be 0, you can conclude that the only possible eigenvalues are lambda equals 2 and lambda equals 3. To figure out what the eigenvectors are that actually have one of these eigenvalues, say lambda equals 2, plug in that value of lambda to the matrix, and then solve for which vectors this diagonally altered matrix sends to 0. If you computed this the way you would any other linear system, you'd see that the solutions are all the vectors on the diagonal line spanned by -1, 1. This corresponds to the fact that the unaltered matrix, 3, 0, 1, 2, has the effect of stretching all those vectors by a factor of 2. Now, a 2D transformation doesn't have to have eigenvectors. For example, consider a rotation by 90 degrees. This doesn't have any eigenvectors, since it rotates every vector off of its own span. If you actually try computing the eigenvalues of a rotation like this, notice what happens. Its matrix has columns 0, 1, and -1, 0. Subtract off lambda from the diagonal elements and look for when the determinant is 0. In this case, you get the polynomial lambda squared plus 1. The only roots of that polynomial are the imaginary numbers, I and -I. The fact that there are no real number solutions indicates that there are no eigenvectors. Another pretty interesting example worth holding in the back of your mind is a shear. This fixes I hat in place and moves j hat 1 over, so its matrix has columns 1, 0, and 1, 1. All of the vectors on the x-axis are eigenvectors with eigenvalue 1, since they remain fixed in place. In fact, these are the only eigenvectors. When you subtract off lambda from the diagonals and compute the determinant, what you get is 1 minus lambda squared. And the only root of this expression is lambda equals 1. This lines up with what we see geometrically, that all of the eigenvectors have eigenvalue 1. Keep in mind though, it's also possible to have just one eigenvalue, but with more than just a line full of eigenvectors. A simple example is a matrix that scales everything by 2. The only eigenvalue is 2, but every vector in the plane gets to be an eigenvector with that eigenvalue. Now is another good time to pause and ponder some of this before I move on to the last topic. I want to finish off here with the idea of an eigenbasis, which relies heavily on ideas from the last video. Take a look at what happens if our basis vector entries of this matrix, like the one from the start of this video, enough so that you can a matrix representing that same transformation, but from the perspective of
What's a cluster? A cluster is several machines acting as one bigger machine. So just one piece of example, let's say that you had some app in your business and that was delivering a critical service to your customers. You could have one piece of hardware underneath.
The following content is
What's a cluster? A cluster is several machines acting as one bigger machine. So just one piece of example, let's say that you had some app in your business and that was delivering a critical service to your customers. You could have one piece of hardware underneath this app, but what you can do with a cluster is you can say, actually, I'm going to create a machine that's actually made up of 3 machines. I'm going to cluster them so they act as one machine delivering this service to your customers. The benefit of this is similar to a plane with several engines. I'm sure you've heard the term that you can remove one engine and the plane can still land safely. And the same is true of clustering. I could have an absolutely critical failure with that 3rd machine, but the cluster will look after the app and the service is delivered to your customer. So it's about availability and resilience in computing. Now, why do we need to know about these 3 devices in the cluster from an asset management point of view? Because if you're doing a sweep of your network, if you're doing inventory and discovering what's on your network, if you're not familiar that you're using clusters, these might just appear as 3 machines with databases and applications on it, which would be radically different for how a cluster might be priced. So you just need to be aware of nodes, as they're called, within a cluster. So just something to be aware of.
is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
I'm reluctant to say good afternoon given the weather, but I'll say it anyway. I guess now we all do know that we live in Boston. And I should say I hope none of you were affected too much by the fire yesterday in Cambridge, but that seems to have been a pretty disastrous event for some. Anyway, here's the reading. This is a chapter in the book on clustering, a topic that Professor Grimson introduced last week, and I'm going to try and finish up with respect to this course today, though not with respect to everything there is to know about clustering. Quickly just reviewing where we were. We're in the unit of the course on machine learning, and we always follow the same paradigm. We observe some set of examples, which we call the training data. We try and infer something about the process that created those examples, and then we use inference techniques, different kinds of techniques, to make predictions about previously unseen data. We call that the test data. As Professor Grimson said, you can think of two broad classes: supervised, where we have a set of examples and some label associated with the example, Democrat, Republican, smart, dumb, whatever you want to associate with them. And then we try and infer the labels. Or unsupervised, where we're given a set of feature vectors without labels, and then we attempt to group them into natural clusters. That's going to be today's topic, clustering. So clustering is an optimization problem. As we'll see later, supervised machine learning is also an optimization problem. Clustering is a rather simple one. We're going to start first with the notion of variability. So this little c is a single cluster, and we're going to talk about the variability in that cluster of the sum of the distance between the mean of the cluster and each example in the cluster, and then we square it. Okay, pretty straightforward. For the moment, we can just assume that we're using Euclidean distance as our distance metric, Minkowski with equals 2. So variability should look pretty similar to something we've seen before, right? It's not quite variance, right? But it's very close. In a minute, we'll look at why it's different. And then we can look at the dissimilarity of a set of clusters, a group of clusters, which I'm writing as capital C, and that's just the sum of all the variabilities. Now, if I divided variability by the size of the cluster, what would I have? Something we've seen before, what would that be? Somebody?
I just thought about something. Maybe I can create something that takes the index, kind of like the same thing that they're doing here, but instead of counting the elements, but then how I can either get it by island or by the element itself, where every time I hit a certain condition, I can make the values of the other nodes equal to the distance. There's some mathematical relationship that puts the distance between the nodes and whatever that thing is. And then I can sort of have a gradient of boundaries in the graph, I think. And that would be... I think that might work to find a fractal pattern in a graph, I think. Because that way, even... it's kind of like gradient descent in a way. But using distance in the graph instead of adapting the line through the data. Yeah. Maybe I'll do that after I eat.
Isn't that just the variance? So the question is, why am I not doing that? If up till now...
Or try to do that, I should say. Because it's probably harder than what I'm thinking. It's going to be harder than what I'm thinking about.
We always wanted to talk about variance. Why suddenly am I not doing it? Why do I define this notion of variability instead of good old variance? Any thoughts? What am I accomplishing by not dividing by the size of the cluster? Or what would happen if I did divide by the size of the cluster? Yes. Absolutely, I'd normalize it. That's exactly what I would be doing. And what might be good or bad about normalizing it? What does it essentially mean to normalize? It means that the penalty for a big cluster with a lot of variance in it is no higher than the penalty of a tiny little cluster with a lot of variance in it. By not normalizing, what I'm saying is I want to penalize big, highly diverse clusters more than small, highly diverse clusters. Okay? And if you think about it, that probably makes sense. Big and bad is worse than small and bad. All right, so now we define the objective function. And can we say that the optimization problem we want to solve by clustering is simply finding a capital C that minimizes dissimilarity? Is that a reasonable definition? Well, hint, no. What foolish thing could we do that would optimize that objective function? Yeah. Yeah, I have the same number of clusters as points. Assign each point to its own cluster. Oops. Oh, almost a relay. The dissimilarity of each cluster would be 0. The variability would be 0, so the dissimilarity would be 0 and I'd solve the problem. Well, that's clearly not a very useful thing to do. So, well, what do you think we do to get around that? Yeah, we apply a constraint. Exactly. And so we have to pick some constraint. What would be a suitable constraint, for example? Well, maybe we'd say, okay, the clusters have to have some minimum distance between them. Or, and this is the constraint we'll be using today, we can constrain the number of clusters. So, all right, I only want to have at most 5 clusters. Do the best you can to minimize dissimilarity, but you're not allowed to use more than 5 clusters. That's the most common constraint that gets placed in the problem. All right, we're going to look at 2 algorithms. Maybe I should say 2 methods because there are multiple implementations of these methods. The first is called hierarchical clustering, and the second is called k-means. There should be an S on the word mean there. Sorry about that. All right, let's look at hierarchical clustering first. It's a strange algorithm. We start by assigning each item, each example, to its own cluster. So this is the trivial solution we talked about before. So if you have n items, you now have n clusters, each containing just one item. In the next step, we find the 2 most similar clusters we have and merge them into a single cluster. So that now instead of n clusters, we have n minus 1 clusters. And we continue this process until all items are clustered into a single cluster of size n. Now, of course, that's kind of silly, because all I want to put them all in a single cluster, I don't need to iterate, I just go wham, right? But what's interesting about hierarchical clustering is you stop it typically somewhere along the way. you produce something called a dendrogram. Let me write that down. At each step here, that shows you what you've merged thus far. We'll see an example of that shortly. And then you can have some stopping criteria. We'll talk about that. This is called agglomerative hierarchical clustering because we start with a bunch of things and we agglomerate them. That is to say, we put them together. All right? Make sense? Well, there's a catch. What do we mean by distance? And there are multiple plausible definitions of distance, and you would get a different answer depending upon which measure you used. These are called linkage metrics. The most common one used is probably single linkage, and that says the distance between a pair of clusters is equal to the shortest distance from any member of one cluster to any member of the other cluster. So if I have two clusters here, and they have bunches of points in them, single linkage distance would say, well, let's use these 2 points, which are the closest, and the distance between these two is the distance between the clusters. You can also use complete linkage, and that says the distance between any two clusters is equal to the greatest distance from any member to any other member. Okay, so if we had the same picture we had before, probably not the same picture, but it's a picture, whoops, then we would say, well, I guess complete linkage is probably the distance maybe between those two. And finally, not surprisingly, you can take the average distance. These are all plausible metrics. They're all used in practice for different kinds of results, depending on the application of the clustering. All right, let's look at an example. So what I have here is the air distance between 6 different cities, Boston, New York, Chicago, Denver, San Francisco, and Seattle. And now let's say we want to cluster these airports just based upon their distance. So we start, the first piece of our dendrogram says, well, all right, I have 6 cities, I have 6 clusters, each containing 1 city. All right, what happens next? What's the next level going to look like? Yeah? I'm going to join Boston and New York, as improbable as that sounds. All right, so that's the next level. And if for some reason I only wanted to have 5 clusters, well, I can stop here. Next, what happens? Well, I look at it and I say, well, I'll join up Chicago with Boston and New York. All right, what do I get at the next level? Somebody? Yeah. Doesn't look like it to me. If you look at San Francisco and Seattle, they are 808 miles, and Denver and San Francisco is 1235. So I end up, in fact, joining San Francisco and Seattle. Ah, well, that explains why I need my hearing fixed. All right, so I combine San Francisco and Seattle, and now it gets interesting. I have 2 choices with Denver. Obviously, there are only 2 choices. And which I choose depends upon which linkage criterion I use. If I'm using single linkage, well, then Denver gets joined with Boston, New York, and Chicago because it's closer to Chicago than it is either San Francisco or Seattle. But if I use complete linkage, it gets joined up with San Francisco and Seattle because it is further from Boston than it is from, I guess it's San Francisco or Seattle, whichever it is, right? So this is the place where you see what answer I get depends upon the linkage criteria. And then if I want, I can consider the next step and just join them all. All right? That's hierarchical clustering. So it's good because you get this whole history of the dendrograms. And you get to look at it and say, well, all right, that looks pretty good. I'll stick with this clustering. It's deterministic. Given a linkage criteria, you always get the same answer. There's nothing random here. Notice, by the way, the answer might not be optimal with regard to that linkage criteria. Why not? What kind of algorithm is this? It's a greedy algorithm, exactly. And so I'm making locally optimal decisions at each point, which may or may not be globally optimal. It's flexible. Choosing different linkage criteria, I get different results, but it's also potentially really, really slow. This is not something you want to do on a million examples. The naive algorithm, the one I just sort of showed you, is n cubed. N cubed is typically impractical. For some linkage criteria, for example, single linkage, there exist very clever n squared algorithms. For others, you can't beat n cubed. But even n squared is really not very good. Which gets me to a much faster greedy algorithm called k-means. Now, the k in k-means is the number of clusters you want. So the catch with k-means is if you don't have any idea how many clusters you want, it's problematical. Whereas hierarchical, you get to inspect it and see what you're getting. If you know how many you want, it's a good choice because it's much faster. All right, the algorithm, again, is very simple. This is the one that Professor Grimson briefly discussed. You randomly choose k examples as your initial centroids. Doesn't matter which of the examples you choose. Then you create k clusters by assigning each example to the closest centroid. Compute k new centroids by averaging the examples in each cluster. So in the first iteration, the centroids are all examples that you started with, but after that, they're probably not examples because you're now taking the average of 2 examples, which may not correspond to any example you have, actually the average of n examples. And then you just keep doing this until the centroids don't move. Right? Once you go through one iteration where they don't move, there's no point in recomputing them again and again and again. So it is converged. So let's look at the complexity. Well, at the moment we can't tell you how many iterations you're going to have, but what's the complexity of one iteration? Well, let's think about what you're doing here. You've got k centroids. Now I have to take each example and compare it to each, naively at least, each centroid to see which it's closest to, right? So that's k comparisons per example. So that k times n times d, where how much time each of these comparisons takes, which is likely to depend on the dimensionality of the features, right? Just Euclidean distance, for example. But this is a way small number than n squared, typically. So each iteration is pretty quick. And in practice, as we'll see, this typically converges quite quickly. So you usually need a very small number of iterations. So it is quite efficient, and then there are various ways you can optimize it to make it even more efficient. This is the most commonly used clustering algorithm because it works really fast. Let's look at an example. So I've got a bunch of blue points here, and I actually wrote the code to do this. I'm not going to show you the code. And I chose 4 centroids at random. It's colored stars. A green one, a fuchsia-colored one, a red one, and a blue one. So maybe they're not the ones you would have chosen, but there they are. And I then, having chosen them, assign each point to one of those centroids, whichever one is closest to. All right? Step 1. And then I recompute the centroids. Let's go back. So we're here, and these are the initial centroids. Now, when I find the new centroids, if we look at where the red one is this point, this point, and this point. Clearly, the new centroid is going to move, right? It's going to move somewhere along in here or something like that, right? So we'll get those new centroids. There it is. And now we'll reassign points. And what we'll see is this point is now closer to the red star than it is to the fuchsia star, because we moved the red star. Oops, that one said the wrong thing. I read to start with. This one is now suddenly closer to the purple. So it's the red. It will get recolored. We compute the new centroids. We're going to move something again. We continue. Points will move around. This time we move 2 points. Here we go again. Notice again the centroids don't correspond to actual examples. This one is close, but it's not really one of them. Move 2 more. We compute centroids, and we're done. So here we converge, and I think it was 5 iterations, and nothing will move.
just remember that there's something else that I want to do that I might do on stream because I think it's worth it, which is to first study compilers and then try to create something that what I was trying to do a long time ago, which is to create a visualization of all the things that exist on a Python library. So loop through all the files and then create the connection between all the functions and represent that in a graph. I think that's going to be really interesting. You can go watch these videos off stream and I'll search for well-known graphs. How can I search for this? Obviously, it's gonna be use this one. These ones I already know. think I'll just watch videos about this 10, whatever, not 10, whatever, how many this is. The thing I was saying about fractals before, I don't know if it makes sense or not. I was thinking about it, and I think it doesn't make a lot of sense what I was talking about, but I'm not sure. What I want to do is find fractals. It's kind of hard to phrase what I'm thinking about trying to do. That's the problem. I don't know if it makes a lot of sense. Because if you have data and you're trying to find a fractal in the way that I was talking about, with changing the weights of each node to be relative to the position of the whatever the data is, you're just gonna represent the data. You're not gonna be able to capture a fractal pattern from that data. That's the thing that I don't think makes sense. And I guess what I'm trying to think more about is, given a set of data or like file structures, for example, in a computer, how can I create a fractal or a multifractal pattern that is close enough to the representation of whatever that thing is? That's what I'm trying to think about. I'm gonna look for these ones that I have here.
Hello guys, my name is Felipe Veloso and this is the third video of the series explaining the work of Benoit Mandelbrot, my idol. And especially this book here, this amazing book called The Misbehavior of Markets. So in the first video, if you watch it, if you didn't watch, just come back and watch. And then in the first video, I explained it in a more high level way, what his work consisted on, the problems he found, the solutions, his observations, in a very high level way, in a very intuitive way. It's going to be fun to watch. Second video, I explained that I'm going to apply one of the papers based on his models, which name is like the multifractal model for predicting volatility of 2019. So you should also come back in the previous videos and watch like 5 minutes. And today I'll talk about another problem that we find in the models that we use today. When I say that we use, I'm saying the industry. And one of this paper that I am replicating is basically trying to get a model that predicts volatility better than the arch and the gauge. So basically, in the previous video, I explained something called long memory. So long memory consists in a correlation, in an autocorrelation, in a persistence through a data of volatility. It means that the large changes are more likely to be followed by large changes, and small changes are likely to be followed by small changes. It means that the observations are not independent. The observations from today will probably impact the observations from tomorrow. So the volatility today will likely impact the volatility of tomorrow. They are not independent. They are not like a random walk, a Brownian motion. So then we analyze, but okay, Felipe, the arch and the gauge, we capture some of this persistence. So okay, I'll draw the volatility clustering. For example, if we see a behavior like this, here we can clearly see clusters. So here we have a little cluster with don't have a model that understands this clustering in this high persistence, this long memory. The model won't work well. And I explained it, as I explained it, the gauge and the arch, they don't consider enough. You know, their the volatility, the correlation, through a volatility series is way more persistent, way more consistent than it applies. It applies a very high fall. It decaying exponentially, and that's not true. So in the next video, I'll explain how the multifractal, actually more specifically, the bivariate two variables multifractal volatility model. I'll replicate the paper that I explained in the previous video. The forest of knowledge.
Hey everyone, and welcome to this video on Dijkstra's shortest path algorithm. Suppose you have a graph connected by weighted edges like this one, then Dijkstra's algorithm allows you to calculate the shortest path from a fixed node to every other node. This can be applied, for example, in digital mapping. So suppose those nodes are cities and the edges are routes between them, then Dijkstra's algorithm will allow you to calculate the distance from one step. We mark all nodes as unvisited, so therefore we create two that change over time. So therefore we can use this table on the right, which consists of 3 columns. In the second column we have the current shortest distance from A to this node. So in the beginning of this algorithm, we know nothing of any distance to any other node than A, so we set A to 0, because the distance from A to A is 0, and every other distance we set to infinity. And in the last column, we store the previous node that leads us to the shortest distance. And this column will be empty in the beginning, because currently we have no information about this. So those are the things we need to track off, and now we can start with the first iteration. Since we start at node A, we start by calculating the distance to all unvisited neighbors of A. The distance from A to B is 2, and the distance from A to D is 8. And now we can update our table on the right if we found a new shorter distance to one of the unvisited nodes. So B and D are unvisited, and the current distance is infinity. So we can update the distance from A to B to 2, and store A as the previous node in our table. And the same applies to the node B. We can update the shortest distance to D to the value of 8, and for the previous node A. And now our iteration ends here, and we can mark A as visited, remove it from our unvisited nodes, and put it in our visited nodes list. The last step we didn't talk about yet is to pick a new node as a current node to explore this graph further. And therefore, we always choose the node with the current minimum distance in all our unvisited nodes. So when you look at our table, we have A with a distance of 0, but A is already visited. We have B as an unvisited node with a distance of 2, and we have D with a distance of 8. All the other nodes have distance infinity. So B has current shortest distance of all unvisited nodes. This means that B becomes our current node. For our node B, we can now go back to our step 3 to calculate the distance of all unvisited neighbors of B. So unvisited neighbors of B are E and D, and the distance calculation works as follows. Since B has a current distance of 2, we need to add this 2 to the weight of the edges to E and D. So now let's first look at the node E. Node E will have the current distance 8 from A over B. And now we need to check if 8 is less than the current shortest distance that we stored in our table. And the current shortest distance we stored in our table is infinity, and 8 is certainly less than infinity, so we update our shortest distance to E and set B as the previous node. Now let's look at the node D. D will now have a distance of 7, 2 plus 5 from A over B. This means we need to compare this 7 to our current value 8 in the table. And since 7 is less than 8, we set the current value for the shortest distance to 7, and we set the previous node to B. Now we are finished with B because we visited all unvisited neighbors of B, and we can mark B itself as visited. In the next step, we choose a new current node from all unvisited nodes again, and we choose the node with the minimum distance. The node with the minimum distance in this case is D because it has a distance of 7. We now calculate the distance to all unvisited neighbors of D, and in this case we need to add 7 to this distance because currently the shortest distance from A to B is 7 when we look at our table. So now we need to consider if we need to update the distance to E or we need to update the distance to F. So let's start with E. The distance from A to E over D is 10, 7 plus 3, but 10 is not less than our current distance 8 that we have stored in our table, so we won't update our distance to E. When we look at the node F, on the other hand, the current distance we have in our table is infinity, but now we get a distance of 9 from A to F over the node D. So we update our shortest distance in the row F, set it to 9, and set the previous node to D. We can now mark D as visited, and we can go on with the next node in the unvisited node list with the current minimum distance, and this would be E, because E has a distance of 8 and F has a distance of 9, and C of infinity. So we calculate the distance from E to C and E to F. And in this case, we need to add 8 to the distance, because 8 is the current distance from A to E. Let's start with the node C. We now have a distance of 17 from A to C over the node E, and this is certainly less than infinity, so we can update our distance to C in our table. Set the shortest distance to 17 and the previous node to E. When we now look at F, we see that we have a new distance of 9 to F, which is exactly the same as our old distance to F, so we don't update anything, and we are finished with our node E. Now we have F and C left as unvisited nodes, and F has a distance of 9 and C has a distance of 17. We always start with the one with the minimum distance, so we start with F, and the only unvisited neighbor is C. And now we see that we have a distance of 12 from A to C if we go over the node F, so we update the shortest distance to C to 12, set the previous node as F, and mark F as visited. This leaves us with node C. Since C has no unvisited neighbors, we're done here, and we can mark C as finished. And now we're done with the algorithm. And in our table, we have some important information about this graph. We have now the shortest distance from A to every other node in this graph, and we have the previous node, which helps us to reconstruct the shortest path. So, for example, if we want to reconstruct the path from A to C, the first thing we see is that the shortest distance is 12. To find the shortest path now, we start at the node C, look at its previous node, which is F in the table. So we mark this node from F to C. And now we look at F and see that it has the previous node D, so we mark this edge from D to F. We now just need to look at the node D in our table. We see that it has the previous node B, so we mark the edge from B to D. And when we look at the node B in our table, we see that it has the previous node A. And now we found a connection from A to C that has the length 12 and is the shortest path. I hope this video helped you to understand the Dijkstra algorithm. If so, please leave a like and subscribe for more computer science and programming videos.
Dijkstra's shortest path algorithm was invented by the late great Edgar Dijkstra, a famous Dutch computer scientist. The objective of the algorithm is to find the shortest path between any two vertices in a graph. In fact, Dijkstra's algorithm will find the shortest path from a given starting vertex to every other vertex in the graph. Consider this simple graph. Our objective is to find the shortest path from A to every other vertex. Once it is run, Dijkstra's algorithm will generate this information, which includes everything we need to know. We have the shortest total distance from the starting vertex to all of the other vertices. The total shortest distance from A to B is 3. From A to C, it's 7. From A to D, 1. And from A to E, it's 2. We also have the shortest sequence of vertices from A to every other vertex. In other words, the shortest path. For example, to get from A to C, notice that we arrived at C via E. This is shown in the previous vertex column. When we examine the information for E, we can see that we arrived at E via D. And when we examine the information for D, we can see that we arrived at D via A. So the previous vertex column actually gives us the shortest path from A to every other vertex. So how does Dijkstra's algorithm go about generating this information? Dijkstra's shortest path algorithm works as follows. We're using two lists, one to keep track of the vertices that we visited, and another to keep track of the vertices that we haven't visited yet. So let's consider the starting vertex, A. The distance to A from A is 0. That seems rather obvious, but you'll see that becomes important a bit later. The distances to all other vertices from A are unknown. So for the purposes of the algorithm, we're going to set them to a very high value, let's say infinity. We can include this information in our table straight away. Now the algorithm begins good and proper. We'll start by visiting the unvisited vertex with the smallest known distance from the start vertex. First time around, this is the start vertex itself, it's A. For the current vertex, we then examine its unvisited neighbours. Well, we're currently visiting A, and its unvisited neighbours are B and D. These are the vertices that A shares edges with. For the current vertex, we calculate the distance of each neighbour from the start vertex. This may seem like overstating the obvious at the moment, but it'll become apparent why we state it like this a little bit later. For now, the distance from A to B is nothing plus 6, which is 6, and from A to D is nothing plus 1, which is 1. If the calculated distance of a vertex is less than the known distance, we can update the shortest distance in our table. Well, at the moment, all of our shortest distances are infinity, so we can update these two distances. Now, we update the previous vertex for each of the updated distances. In this case, we visited B and D via A, so we'll write this information into the previous vertex column. Now, add the current vertex to the list of visited vertices. We won't be visiting A again. Now the algorithm begins to repeat. Visit the unvisited vertex with the smallest known distance from the start vertex. This time around, we can see in the table that it's vertex D. For the current vertex, examine its unvisited neighbours. We're currently visiting D, and its unvisited neighbours are B and E. For the current vertex, calculate the distance of each neighbour from the start vertex. The distance of B from A is the one which we've already written into the table, the distance from A to D, plus another 2, giving us a total distance of 3. The distance from A to E is the distance from A to D, which we've already calculated and written into the table, 1, plus another 1 from D to E, giving us a total distance of 2. If the calculated distance of a vertex is less than the known distance, update the shortest distance. The shortest known distance from A to B, as written in the table, is 6. We just calculated a new shortest distance of 3. The shortest known distance from A to E, as per the table, is infinity. And again, we've calculated a much shorter distance from A to E, so we can write these values into the table, replacing the previous values. We found some shorter paths. Now, we update the previous vertex for each of the updated distances. In this case, we visited B and E via D, so we write this information into the table. Add the current vertex to the list of visited vertices. We won't be visiting D again. And once again, visit the unvisited vertex with the smallest known distance from the start vertex. This time around, the information in the table tells us that it's vertex E. For the current vertex, examine its unvisited neighbours. We're currently visiting E, and its unvisited neighbours are B and C. For the current vertex, calculate the distance of each neighbour from the start vertex. And again, using the information in the table, we can see that the total distance to B is 2 from the table, the distance to E, plus another 2, giving us 4. And we can see that the total distance to C from A is 2, the distance to E from the table, plus another 5, giving us a total of 7. If the calculated distance of a vertex is less than the known distance...
I think I'll watch these videos off stream about these graphs here. I need to think more about... I want to study the data structures and algorithms, but I don't... to be honest, I don't think that's my style of learning. I just don't like doing this that much. It feels um, it seems to me that it's not the most effective way to learn for me. I think it's better if I find something that I want to build and then I incorporate these structures into what I'm building. I think that's a better approach, but I have to spend more time thinking about what I can do that is related to blockchains. And yeah, because the biggest problem is that I don't have the data yet, but it has to be related to blockchains and something that is involved with trees or graphs that I can build. And I'm thinking about a bunch of different things. So I think what I'm gonna do is study this stuff off stream, and I'm gonna study the Lighthouse project on stream, and I think I'm gonna read these articles as well. Yeah, but I'm gonna start with searching for the Lighthouse. I'm gonna study the Lighthouse code on stream until I can think about something that I can do. I also have to finish this. Something that I can do that is gonna involve building graphs and or graphs or trees. And I am thinking about the thing about the clusters there was really interesting to me. I was thinking about building a matrix and then creating something that puts a weight on the nodes of the matrix related to some data, and then trying to find the clusters on that. So pretty much trying to implement the k-means algorithm, but in a different way. I was thinking about. And also, I want to do something that is involved with fractals because I think fractals and multifractals are everything. Everything's a multifractal, pretty much. But it's hard to think about. Because the issue is all of the stuff that I think about involves physics, and then I think it's gonna be really hard, and I might not finish the project or it's not even that I might not finish, it's that I have to think more about exactly the relationships that I'm thinking about so that once it's more clear, I know kind of what I have to build. Because I'm thinking about the relationship between gravity and the clusters and fractals. I think these things are all related, but I'm not really sure how. I think that clusters are formed because of the law of gravity, but I don't know. And then that creates fractals. That's what I'm thinking, but I don't know how to incorporate that in relationship to data about something, maybe blockchains, to capture, because I think that everything is gonna have fractal patterns in it, and including the blockchain. But then the abstraction part is easy, but then how do you put that on a format? Because I know that it's probably gonna follow Pareto distribution. The clusters of the blockchain are probably gonna follow Pareto distribution, which means that most of the transactions are done by 20% of the accounts. But how do I think about creating an algorithm that is able to capture, let's say, the growth of the chain based on the cluster and incorporate physics into that, the gravity, density, and stuff like that. That's really because in the concepts is easy, but how I'm gonna translate the Pareto distribution to whatever I want to do. Do I do a equation like y equals 1 divided by x, or like the Uniswap equation for exponential, or do I use something else? Or do I get the data and then from the data try to derive something? It's hard to think about a way to phrase or to frame it so that I can try to build something on string with it. And just watching the videos is kind of boring. Where's the book? Let's start now. Okay. I think that's the whole project. I'm just gonna clone this. I think I had the project before, but then I deleted it. Oh. Oh fuck, I think I thought it was finished, but it seems like it wasn't. Try that again. Okay. I think I'm gonna finish this. Where is it? this stuff here first before the timer runs out. And what can I do about it? About what can I build that is gonna require a graph and a graph for trees and fractal patterns and the blockchain? That's what I have to think about it. Most of these are the same as the other one. Control C. Ouais. Not sure. Top. Yeah, this one is SP or PS. Yeah, PS. I think I'm gonna test this. Most of them are the same, so next I think is no. No, I don't remember. I don't know if it's move file. I'm not sure. And this one I don't remember if it's like this. I think it is like this. Yeah. Previous commands. Fuck. Or maybe this is up. I think I got one of them wrong because I typed top on them, but I think this one is the top. Oh, maybe that one was who am I actually. This one is W. So I messed the other one up, I think. I don't remember this one. Show command history. Yeah, I don't know. Isn't the app? I also don't know this one. Free disk space. Maybe it's a new one? I know it's not free because free is the other one. Yeah, I have no idea. So pass. I passed, but I failed a bunch of them. And his move with more file. I got these ones twisted as well. This one was a new one actually. History. Oh, it was the F. So I was correct. Yeah. Okay, last one. Fuck. Or maybe spias. That makes sense. I wanna test this one. If I pass, I think I'm gonna stop here. I just wanted to stream today to maintain some level of consistency. But I'm more focused on the stuff that I'm doing off stream. That's why I wanted to do lead codes. I thought would be a good idea. I have no idea. This one. Is this something like this? I have no idea as well. So, dar. I don't know. I have no idea. This one I'm not sure if I'm messing it up again. Mixing the two of them. I think I am. I think this is probably 5. I have no idea as well. Yeah, I don't remember. I know it's something with tar. With X. I have no idea. Something like this. This is either top or I think it's top. Recent commands. Drawer. Oh, I always confuse that one with the background. It's Control Z. Oh, I think I messed the other one up as well, because this one is cat file. I don't know. Maybe. Yeah, I don't know this one. This one is PS, I think. Oh, and I think I messed it up. This one is Control D, the other one is Control H. Maybe. Yeah, maybe it's like this. Beginning of the line. Okay, I got a bunch of them wrong, but I passed. Also, I got this one incorrectly. Yeah, but I had no idea. Whatever. I think I'm gonna stop here. Like I said before, I just wanted to stream today to maintain some level of consistency. But I didn't have any ideas what to do because I want to do things that are more related to what I'm doing off stream. And that involves data structures and algorithms and also the blockchain. I think next time I'm going to study this project from Lighthouse. It's going to depend on whether or not I have the data, which I probably won't. Or I will try to think about something that I can do that involves graphs. I'm going to study all these graph algorithms off stream as well. I'm going to watch videos about them and watch these videos here. And yeah, I want to do something that involves graphs, fractals, and the blockchain, probably. But I have to think more about a project or something that I can do on stream. So next time I'm either gonna do that or I might go back to do the poker stuff. But like I said, I wanna do something that is more involved with the blockchain so I don't lose a lot of focus. But I don't know, I'll probably go back and forth between the two. So yeah.